into a space where learning meets relaxation. Find a cozy spot, lean back, and let the gentle rhythm of this tutorial start to wash over you. Take a deep breath, let go of the day's worries, and let the words flow like a soothing melody. As we explore the world of SQL, may your mind wander gently through the lessons, and may your curiosity be met with calm. If you're feeling the calm, hit that like button and subscribe for more tranquil coding journeys. Let's begin. Welcome to the first session of our SQL Programming Language Training course. Today, we will explore the fundamentals of SQL and databases, which are essential tools for managing and analyzing data in modern technology. This session will cover the core concepts of databases, the role of SQL in data management, and why these skills are crucial for data professionals. By the end of this session, you will have a clear understanding of how databases and SQL work together to store, retrieve, and manipulate data efficiently. Let's begin by diving into what a database is and how it functions. A database is an organized collection of structured data that is stored and managed in a way that allows for efficient retrieval, updating, and management. Think of it as a digital filing cabinet where information is categorized and stored logically. For example, a customer records database might store details like names, addresses, and purchase histories, while an inventory system could track product stock levels and sales data. Databases are designed to handle large volumes of information and ensure that data remains consistent and accessible. They form the backbone of many applications, from banking systems to social media platforms, making them a critical component of modern computing. A database management system, or DBMS, is software that acts as an intermediary between users and databases. It provides tools to create, manage, and secure databases while ensuring data integrity and performance. For instance, a DBMS like MySQL allows users to define database structures, control access to data, and enforce rules to prevent errors. It also handles tasks like backup and recovery, which are vital for protecting data from loss. Popular examples of DBMS include MySQL, Oracle, and PostgreSQL, each offering unique features tailored to different use cases. By using a DBMS, organizations can maintain control over their data while enabling seamless interaction with it. Structured Query Language, or SQL, is the standard language used to interact with relational databases. allows users to perform a wide range of operations, from querying data to modifying database structures. For example, SQL enables you to retrieve specific information from a database, such as all customers who made purchases in the last month, or to update records when new data becomes available. Its standardized syntax makes it widely applicable across different database systems, ensuring consistency and ease of use. Whether you are analyzing data for business insights or building applications that rely on databases, SQL is an indispensable tool for any data professional. Databases are structured around three primary components: tables, rows, and columns. A table is like a spreadsheet, organizing data into rows and columns. Each row represents a record, such as a single customer entry, while columns define the attributes of that data, like name, email, or phone number. For example, a table storing employee information might have columns for employee ID, full name, department, and salary. This structured format ensures that data is stored in a logical and searchable way, making it easier to manage and analyze. Understanding these components is the first step toward mastering SQL and database interactions. SQL plays a central role in data management by enabling users to query, update, and maintain databases. It allows you to extract specific data for analysis, such as finding the total sales for a particular product. SQL also lets you modify existing data, like updating a customer's address, or delete outdated records to keep the database clean. Additionally, it supports creating and modifying database structures, such as adding new tables or changing column types. These capabilities make SQL a powerful tool for managing data throughout its life cycle, from storage to retrieval and beyond. There are several key SQL commands that form the foundation of database interactions. The select command retrieves data from a database, such as all records in a customer table. The insert command adds new records, like a new customer entry. The update command modifies existing data, for instance, changing a customer's email address. The delete command removes records that are no longer needed, and the create command defines new database structures, such as tables or indexes. Mastery of these commands is essential for anyone working with databases, as they form the basis of most data operations. In today's data-driven world, SQL is an essential skill for professionals across industries. financial institutions use SQL to analyze transactions and detect fraud, while healthcare providers rely on it to manage patient records and track treatment outcomes. Tech companies leverage SQL for data analytics, enabling them to make informed decisions based on user behavior. Moreover, SQL serves as the foundation for big data technologies and artificial intelligence, where it is used to process and analyze vast data sets. As data becomes increasingly central to decision-making, proficiency in SQL opens up opportunities in a wide range of fields. To summarize, SQL is the cornerstone of relational database interaction, providing the tools needed to store, retrieve, and manage data effectively. Understanding databases and SQL is critical for anyone pursuing a career in data science, software development, or business analytics. In the next session, we will delve into basic SQL syntax and learn how to write queries to extract meaningful insights from data. Stay tuned, and let's continue exploring the power of SQL together. The purpose of installing a database system is to create a structured environment for storing, managing, and retrieving data efficiently. A database management system serves as the core software that handles all interactions with the data, while client tools allow users to communicate with the database. Configuration files define how the system operates, ensuring consistency and customization. Proper setup is critical because it lays the foundation for all SQL operations, impacting performance, security, and scalability. Without a well-configured database, even the most complex queries may fail or perform poorly. When choosing a database system, it is essential to evaluate options like MySQL, PostgreSQL, and SQL Server based on specific needs. MySQL is known for its ease of use and scalability, making it ideal for web applications. PostgreSQL offers advanced features such as support for complex queries and geospatial data, appealing to developers requiring flexibility. SQL Server excels in enterprise environments with robust tools for integration and analytics. Factors such as scalability, which refers to the ability to handle growing data, features like support for specific data types, licensing costs, and community support for troubleshooting should guide the decision. Selecting a system that aligns with project requirements and team expertise ensures long-term efficiency and reduces potential complications. The installation process begins by downloading the database management system from its official website to ensure authenticity and access to the latest updates. Once the installer is obtained, running it initiates the setup wizard, which guides users through the installation steps. During this phase, it is important to select the necessary components, such as the server, client tools, and documentation, depending on the intended use. After installation, verification is crucial. This can be done via the command line by executing commands like MySQL version, or using graphical user interface tools to confirm the system is operational. A successful installation ensures that subsequent configuration and testing can proceed without interruptions. Configuring the database involves several key steps to tailor the system to specific requirements. Setting up user accounts and permissions ensures that only authorized individuals can access or modify data, enhancing security. Storage paths and memory allocation must be adjusted to optimize performance, particularly for large datasets. Network settings may need to be configured for remote access, allowing users to connect from different locations. But this requires careful management to prevent vulnerabilities. Finally, initializing the database instance prepares it for use by creating the necessary structures and initializing default settings. These steps are vital for ensuring the database functions as intended and meets the demands of the application it supports. Security is a top priority when working with databases. Using strong passwords for administrative accounts prevents unauthorized access, while enabling encryption for data at rest and in transit protects sensitive information from potential breaches. Regular backups are essential to recover data in case of hardware failure or cyber attacks, and storing backups in secure, off-site locations adds an extra layer of protection. Restricting access to sensitive operations, such as modifying system tables or executing administrative commands, minimizes the risk of accidental or malicious changes. By implementing these best practices, organizations can safeguard their data and maintain compliance with security standards. After installation, initial setup tasks help verify that the database is ready for use. Creating a test database and user allows for experimentation without affecting production data. Important Importing sample data or a schema provides a practical environment for learning and testing queries. Using client tools like MySQL Workbench or PG Admin to test connectivity ensures that the database is accessible and functioning correctly. Validating basic SQL commands such as select, insert, and update confirms that the system is operational and that users can interact with the database as expected. These tasks lay the groundwork for more advanced database management. Troubleshooting common issues is an essential skill for database administrators. If installation errors occur, checking the system logs can reveal the root cause, while ensuring the system meets the minimum requirements prevents compatibility issues. Connection problems often stem from incorrect port settings or firewall rules blocking access. So verifying these configurations is critical. Configuration mistakes, such as misconfigured parameters in files like my.cnf, can be resolved by carefully reviewing and adjusting the settings. When faced with challenges, referring to official documentation or community forums provides valuable insights and solutions. Proactive troubleshooting ensures minimal downtime and keeps the database running smoothly. In summary, the key steps for setting up a database include installation, configuration, and implementing security measures. A stable database environment is crucial for reliable data management and application performance. Practicing with real-world scenarios enhances understanding and prepares users for challenges they may encounter. As we move forward, the next session will focus on writing basic SQL queries, building on the foundation established today. This will enable you to interact with databases effectively and begin exploring their full potential. Databases are essential tools for organizing information in a structured way so that data can be stored and accessed efficiently. Imagine a library where books are neatly arranged by category, author, and title. Similarly, databases use structured formats to ensure that data is easy to find and manage. The key components of a database include tables, which are like digital spreadsheets, rows that represent individual records, and columns that define the specific attributes of those records. Relationships between these elements allow data to be connected and queried effectively. Relational databases, which are the most common type, use SQL as their primary language for managing and retrieving data. Understanding these structures is crucial because because it helps in designing databases that are both functional and performant, ensuring that queries run smoothly and data is accurate. A table is a fundamental building block of a relational database designed to hold related data in a systematic way. Think of a table as a grid where each row corresponds to a specific record, such as a customer, and each column represents a particular piece of information about that record, like the customer's name or email address. For example, a customer table might have columns for name, email, and phone number, with each row containing the details of a unique customer. The structure of a table is defined by its schema, which outlines the data types and constraints for each column, and the actual data stored within it. This organization allows for efficient data management, making it easy to add, update, or retrieve information as needed. Primary keys and foreign keys are critical elements that help maintain the integrity and relationships within a database. A primary key is a unique identifier for each row in a table, ensuring that no two rows are identical. For instance, in a customer's table, the customer ID might serve as the primary key, guaranteeing that each customer has a distinct identifier. A foreign key, on the other hand, is a field in one table that links to the primary key of another table, creating a connection between them. For example, an orders table might use a customer ID as a foreign key to associate each order with the correct customer. These keys are essential for enforcing data consistency, preventing orphaned records, and enabling complex queries that span multiple tables. Database relationships define how data in one table is connected to data in another, and they are categorized into three main types. A one-to-one relationship occurs when a single record in one table is linked to exactly one record in another table. For example, a user might have a single profile, and each profile belongs to only one user. A one-to-many relationship is more common, where a single record in one table can be associated with multiple records in another. For instance, a customer can place multiple orders, but each order is tied to only one customer. Finally, a many-to-many relationship exists when multiple records in one table are connected to multiple records in another table. This often requires a junction table to manage the connections, such as in a scenario where students can enroll in multiple courses, and courses can have multiple students. Normalization is a process used to organize data in a database to reduce redundancy and improve data integrity. The first step, first normal form, involves eliminating duplicate data and ensuring that each column contains atomic values, meaning that each cell holds only a single piece of information. For example, a table storing customer addresses should not have a single column for both street and city. Instead, these should be separate columns. The second normal form builds on this by removing partial dependencies, which occur when a column depends on only part of a composite primary key. This often involves splitting a table into smaller, more focused tables. The third normal form goes further by eliminating transitive dependencies, where a column depends on another non-key column. By following these steps, databases become more efficient, scalable, and easier to maintain. SQL provides several commands to create, modify, and manage database structures. The create table command is used to define a new table by specifying its name, columns, and data types. For example, the command create table customers id primary key, name varchar 50 creates a table called customers with an integer ID as the primary key and a variable character field for the customer's name. The alter table command allows for modifications to an existing table, such as adding a new column or changing the data type of an existing one. This is useful when requirements change over time. The drop table command permanently deletes a table and all its data, which is typically used when a table is no longer needed. These commands form the foundation of database design and maintenance, enabling developers to structure data effectively. In summary, understanding database structures is the cornerstone of effective SQL programming. Tables serve as the primary containers for data, while keys and relationships ensure that data is connected and consistent across the database. Normalization plays a vital role in eliminating redundancy and ensuring data accuracy, which is essential for large-scale applications. By mastering the commands used to create and modify database structures, you can build robust systems that handle complex data requirements. Practice is key to reinforcing these concepts, so take the time to experiment with creating tables, defining relationships, and applying normalization techniques. As you gain experience, you'll find that a solid understanding of database structures makes it easier to write efficient queries and solve real-world data challenges. SQL is a powerful language designed specifically for interacting with relational databases. These databases store data in structured tables, which are made up of rows and columns. When you write SQL queries, you can retrieve, update, or manage data stored in these tables. This session will focus on the fundamental syntax needed to query data effectively. Understanding these basics is essential for anyone looking to work with databases, as they form the foundation for more advanced operations like joining tables or manipulating data. Whether you're analyzing sales figures or searching for specific records, mastering these concepts will enable you to extract meaningful information from your data. The select statement is one of the most commonly used commands in SQL. It allows you to retrieve specific data from a database table. The basic syntax is select followed by the column names you want to retrieve, then from and the table name. For example, if you have a table called users, you could select the name and age columns by writing select name, age from users. If you want all the data from a table, you can use an asterisk, which acts as a wildcard to represent all columns. So select from employees would return every column in the employees table. This flexibility makes the select statement a cornerstone of data retrieval. The from clause is crucial because it tells the database where to find the data you want to retrieve. Without specifying a table, your query would not know which data to access. For instance, select from orders would fetch all records from the orders table. To make queries more concise, especially when dealing with long table names, you can use aliases. An alias is a temporary name assigned to a table, such as C for customers. This not only shortens the query, but also improves readability, especially when working with multiple tables. Always ensure the from clause is correctly placed to avoid errors. The where clause is used to filter records based on specific conditions. It allows you to narrow down the data you retrieve by applying criteria. The syntax involves selecting the columns you want, then specifying the table and the condition. Common operators include equals, greater than, less than, like for pattern matching, between for ranges, and in for multiple values. For example, select from products where price 100 would return all products costing more than 100. This clause is essential for focusing on relevant data and avoiding unnecessary information. Always test your conditions to ensure they return the expected results. Sorting query results is achieved using the order by clause. This allows you to arrange the output in a specific order, either ascending or descending. By default, the order is ascending, which means numbers go from smallest to largest and text from A to Z, for example. Select name from student's order by grade desk would display student names in descending order of their grades. Sorting is particularly useful when presenting data to users or analyzing trends. You can sort by multiple columns, and the order of columns in the clause determines the priority of sorting. Combining clauses like select, from, WHERE, and order by allows you to create complex queries that extract precise information. For instance, you might retrieve specific columns from a table, filter the results based on certain conditions, and then sort the output. An example query could be select name, salary from employees, where department equals HR, order by salary desk, which lists HR employees by their salary in descending order. Parentheses are useful for grouping conditions in the where clause, ensuring that logical operators like and or are applied correctly. This combination of clauses makes SQL a versatile tool for data analysis. By now, you should have a solid understanding of the basic SQL syntax, including select, from, WHERE, and order by. These elements are fundamental for filtering, sorting, and retrieving data efficiently. Practice is key to mastering these concepts, so try writing queries for different scenarios. Whether you're working with small data sets or large databases, these skills will help you navigate and analyze data effectively. As you progress, you'll build on these foundations to tackle more advanced topics like joins and subqueries. Keep experimenting and refining your queries to become more proficient. The select statement is a fundamental tool in SQL used to retrieve data from a database. It serves as the primary method for querying information, allowing users to access the data they need. Whether you want to fetch all the data in a table, specific columns, or rows that meet certain criteria, the select statement provides the flexibility to do so. For example, you can retrieve every column by using the asterisk symbol, or specify individual columns to narrow down the results. The basic syntax of the select statement includes the columns you want to retrieve, the table you are querying from, and optional clauses like where and order by to refine the data further. Understanding this structure is essential for building effective queries that extract meaningful information from databases. The basic syntax of the select statement includes two main variations. Using select star, which is select, retrieves all columns from a specified table. This is useful when you need a complete view of the data, though it may not always be the most efficient approach for large data sets. Alternatively, selecting specific columns, such as select employee name, allows you to focus on the data that is relevant to your needs. This method is often preferred for performance and clarity. The FROM clause identifies the source table for the data, ensuring the query knows where to look. For instance, the query select employee name from employees would return only the employee IDs and names from the employees table, making it easier to work with specific information without unnecessary data. Filtering data with the where clause is a powerful way to narrow down results based on specific conditions. The where clause allows you to apply logical expressions to select only the rows that meet certain criteria. Common operators used in these conditions include equals, less than, greater than, and more. For example, the query select from products where price 100 would return all products with a price exceeding 100. Additionally, the where clause supports more complex conditions by combining them with logical operators like and or. This enables users to create precise filters, such as selecting products that are both priced above 100 and belong to a specific category. Mastery of the where clause is crucial for efficiently retrieving targeted data. Wildcards in the where clause provide a flexible way to search for patterns in text data. The percent symbol, which is a wildcard, matches any sequence of characters, making it ideal for partial matches. For instance, the condition like %, would find all names starting with the letter A. Another wildcard, the underscore, matches a single character. So like A would find names with A as the first character, followed by exactly one more character. These tools are particularly useful when dealing with text fields where exact matches may not be feasible. For example, the query select from customers where name like J% would retrieve all customers with names beginning with J, demonstrating how wildcards can simplify searches for incomplete or variable data. Sorting results with the order by clause ensures that your query output is organized in a logical sequence. This clause allows you to sort data in ascending or descending order, depending on your needs. By default, the sorting is in ascending order, but you can explicitly specify this with the ASC keyword. For descending order, the DESC keyword is used. For example, the query select from orders order by order date DESC would display the most recent orders first. Additionally, you can sort by multiple columns to create more nuanced groupings, such as sorting by date and then by amount. This capability enhances the readability and usability of query results, making it easier to analyze and interpret data. The select statement is the cornerstone of data retrieval in SQL, and mastering its components is essential for effective database querying. Understanding how to filter data with WHERE, search for patterns using wildcards, and sort results with order by significantly improves your ability to extract valuable insights. Practice is key to becoming proficient, as writing and refining queries helps reinforce these concepts. Always take the time to validate your results to ensure they are accurate and relevant to your objectives. By applying these techniques consistently, you can efficiently navigate and manipulate data to meet the needs of your projects or analyses. The where clause is a fundamental component of SQL that allows you to filter records based on specific conditions. When you query a database, you often need to retrieve only the data that meets certain criteria, and the where clause is the tool that enables this. It is used across various SQL statements such as select, which retrieves data, update, which modifies existing records, and delete, which removes data. By applying conditions in the where clause, you can ensure that your queries return only the relevant information, making your data interactions more efficient. This filtering capability is essential for working with large data sets, as it prevents unnecessary data retrieval and reduces processing time. Mastering the where clause is a critical step in becoming proficient in SQL programming. Comparison operators are the building blocks of conditions in the where clause. These operators allow you to compare values and determine how they relate to each other. For example, the equals sign is used to check if a value is exactly equal to another. The not equal to operator can be written as either equals or depending on the SQL dialect, and it is used to exclude records that match a specific value. The greater than operator, represented by, identifies values that that are larger than a given number, while the less than operator finds values smaller than a specified value. The greater than or equal to operator equals, and the less than or equal to operator expand these comparisons to include equality. For instance, if you want to find all employees with a salary greater than $50,000, you would use the operator in your where clause. These operators form the basis of many queries and are essential for precise data filtering. Logical operators in the where clause allow you to combine multiple conditions to refine your data filtering. The AND operator is used to ensure that all specified conditions are true. For example, if you want to find customers who live in New York and are active, you would use AND to combine these two criteria. The OR operator, on the other hand, allows you to select records that meet at least one of the conditions. This is useful when you want to include data that satisfies any of several possibilities. The NOT operator negates a condition, enabling you to exclude specific records. For instance, if you want to find all users who are not administrators, you would use NOT. These logical operators work together to create complex and flexible queries, making it possible to address a wide range of data retrieval needs. String pattern matching in SQL is achieved using the like operator along with wildcards. The percent symbol percent acts as a wildcard that matches any sequence of characters, making it ideal for partial matches. For example, if you search for products with names starting with laptop, the pattern laptop percent would return all such entries. The underscore is another wildcard that matches exactly one character, allowing for more precise pattern matching. For instance, lap could match laptop if the pattern requires a specific length. When dealing with special characters that might interfere with the wildcard syntax, the escape keyword is used to indicate that a character should be treated as a literal. This feature is particularly useful when searching for values that contain characters like percent or in their actual data. String pattern matching is a powerful tool for querying text-based data efficiently. Practical examples demonstrate how the where clause can be applied in real-world scenarios. When filtering data with multiple conditions, you can use logical operators to combine them. For example, retrieving orders placed after a specific date and marked as shipped requires the AND operator to ensure both conditions are met. This approach helps in isolating the exact data needed for analysis or reporting. Another common use case is excluding specific records using the not operator. For instance, selecting all users who are not administrators ensures that sensitive data or actions are restricted to authorized roles. These examples highlight how the where clause can be tailored to meet diverse requirements, making it a versatile tool for data management. By experimenting with different combinations of operators and conditions, you can develop a deeper understanding of how to structure effective queries. Adhering to best practices when using the where clause can significantly enhance query performance and readability. One key recommendation is to use indexes on columns that are frequently used in where conditions. Indexes act as pointers to data, allowing the database to locate records more quickly and reducing query execution time, avoiding the use of leading wildcards, such as %value. In-like patterns is another important consideration, as this can prevent the database from utilizing indexes effectively and slow down searches. Testing conditions on small datasets before applying them to large tables helps identify potential issues early, ensuring that your queries behave as expected. Additionally, using parentheses to group complex logical conditions improves clarity and reduces the risk of logical errors. By following these practices, you can create more efficient, maintainable, and accurate SQL queries. In conclusion, the where clause is an indispensable tool in SQL for filtering and manipulating data. Its ability to apply conditions makes it a cornerstone of data retrieval and modification. By mastering comparison and logical operators, as well as string pattern matching techniques, you can construct precise and powerful queries. Applying best practices such as indexing, avoiding inefficient patterns, and testing your conditions ensures that your queries are both effective and optimized. Finally, practicing with real-world scenarios helps solidify your understanding and prepares you to tackle complex data challenges. The where clause is not just a feature of SQL. It is a fundamental skill that every programmer should develop to work efficiently with databases. Sorting arranges query results in a specific order to make data easier to understand and analyze. For example, if you have a list of employees, sorting by their names or salaries can help quickly locate specific information. Limiting restricts the number of rows returned by a query, which is especially useful when dealing with large datasets. By combining both sorting and limiting, you you can enhance the readability of your results and improve the performance of your database operations. These techniques are fundamental for efficiently managing and presenting data in SQL. The order by clause is used to sort the results of a query based on one or more columns. The basic syntax is order by column name, which by default sorts in ascending order. If you want to sort in descending order, you can specify the keyword desk. For instance, if you want to see the highest salaries first, you would use order by salary desk. This clause is essential for organizing data in a way that aligns with the needs of the user or the requirements of the analysis being performed. Sorting by multiple columns allows you to create a hierarchy of order in your results. The syntax for this is order by column 1, column 2, and so on. The first column listed is the primary sort key, and the second column is the secondary key. For example, if you sort orders by customer ID and then by order date, all orders for each customer will be grouped together, and within each group, the orders will be arranged in chronological order. This is particularly useful when you need to analyze data with multiple criteria, such as grouping sales by region and then by date. Limiting results is achieved using the limit keyword in databases like MySQL and PostgreSQL, while SQL Server uses the top keyword. These clauses are designed to restrict the number of rows returned by a query, which can prevent overwhelming the user with too much data at once. For example, if you want to retrieve only the top 10 products based on sales, you would use limit 10. This is especially helpful when working with large tables, as it reduces the amount of data processed and improves query performance. Sorting and limiting have practical applications in real-world scenarios. Sorting helps identify trends, such as the highest or lowest values in a dataset, which can inform business decisions. Limiting results ensures that queries are efficient and manageable, especially when dealing with thousands or millions of records. Combining these techniques with the where clause allows for even more precise data retrieval. For example, you might sort sales data by region and then limit the results to the top 5 regions to focus on the most profitable areas. Sorting and limiting are essential tools for improving the efficiency and usability of SQL queries. The order by clause provides structured data organization, while limit and top offer control over the volume of results. Mastering these features enables users to analyze data more effectively and optimize database performance. Whether you are generating reports, debugging queries, or preparing data for further processing, these techniques are invaluable for any SQL practitioner. When working with databases, it's common to have data spread across multiple tables. For instance, customer information might be in one table while order details are in another. To analyze this data effectively, we need to combine information from different tables. This process is called joining tables. The foundation of joining lies in understanding relationships between tables, such as primary keys and foreign keys. A primary key uniquely identifies a record in a table, while a foreign key links to the primary key in another table. By using joins, we can retrieve data that spans multiple tables efficiently. This approach reduces redundancy because we don't have to duplicate data across tables. Instead, we can store data once and access it through relationships, making our database more organized and easier to manage. SQL offers several types of joins to handle different scenarios. The first is the inner join, which returns only the rows that have matching values in both tables. If a record in one table doesn't have a corresponding entry in the other, it won't appear in the result. Then there's the left join, which includes all the rows from the left table and any matching rows from the right table. If there's no match, the result will still show the left table's row with null values for the right table's columns. Similarly, the right join does the opposite, including all rows from the right table and matching rows from the left. Lastly, the full outer join combines both left and right joins, returning all rows from both tables. If there's no match, the missing side will show null values. Each type of join serves a specific purpose, and choosing the right one depends on what data you need to retrieve. The inner join is one of the most commonly used joins. Its syntax is straightforward. You start with the select statement, then specify the tables you want to join using the inner join clause. The key part is the on clause, which defines the condition for the join. For example, if you have a customer's table and an orders table, you might join them on the customer ID. This ensures that only orders with a valid customer ID are included. An example of this is retrieving customer names along with their order details for a specific customer. The inner join is ideal when you want to focus only on records that have corresponding entries in both tables. It helps avoid unnecessary data that doesn't meet the join condition, making queries more precise. The left join and right join are useful when you want to ensure that all records from one table are included, regardless of whether they have matches in the other table. For instance, if you're listing all customers, even those without any orders, a left join would be appropriate. This is because the left table, which in this case is the customer's table, will have all its rows displayed. If a customer has no orders, the order-related columns will show as null. Similarly, a right join ensures all rows from the right table are included. However, right joins are less commonly used because they can often be rewritten as left joins by swapping the order of the tables. The key takeaway is that left and right joins are essential for scenarios where you need to preserve all data from one side of the join, even if there are no matches on the other side. The full outer join is a combination of left and right joins. It returns all rows from both tables, filling in null values for any columns that don't have a match. This type of join is particularly useful for comparing data between tables to find discrepancies. For example, if you're trying to identify customers who don't have any orders or orders that don't belong to a customer, a full outer join would highlight those cases. However, it's important to note that not all database systems support full outer joins. In such cases, you can simulate the result by combining left and right joins with a union operation. Despite this limitation, the full outer join remains a powerful tool for comprehensive data analysis. Using aliases and on clauses can make your SQL queries more readable and efficient. Aliases are shorthand names for tables, which are especially helpful when working with long or complex table names. For example, instead of writing customers and orders every time, you can use T1 and T2 as aliases. The on clause is where you specify the exact condition for the join, such as matching customer IDs between tables. This is different from the where clause, which is used for filtering data after the join. An example of this is selecting customer names and order IDs by joining the customers and orders tables. By using aliases and clearly defining the on clause, you can write cleaner, more maintainable queries that are easier to understand and debug. Subqueries can be used within joins to filter data dynamically. This is especially useful when you need to apply complex conditions before performing the join. For instance, you might use a subquery to select specific records from one table based on a condition, and then join those results with another table. An example is joining the customer's table with a subquery that filters orders based on a specific date range. This allows you to focus on relevant data without including unnecessary records. Subqueries in joins can also improve performance by reducing the dataset early in the query process. However, it's important to ensure that the subquery is properly structured to avoid errors or unexpected results. Let's look at some practical examples of how joins are used in real-world scenarios. The first example involves joining the employees and departments tables to retrieve employee details along with their department information. This helps in generating reports that show which employees belong to which departments. The second example combines sales and product data to create a report on sales performance, including product names and quantities sold. This allows businesses to analyze which products are performing well. The third example demonstrates using multiple joins to retrieve nested data, such as customers, their orders, and the products in those orders. This showcases how joins can be combined to access data across several tables, providing a comprehensive view of the information stored in the database. Mastering joins is essential for efficient data analysis and retrieval in SQL. Each type of join serves a unique purpose, and understanding when to use them can significantly impact the accuracy and performance of your queries. Practicing with different join types in various scenarios will help you become more proficient. It's also crucial to validate your join conditions to ensure they are correct and avoid issues like incorrect results or slow query performance. By taking the time to learn and apply joins effectively, you'll be better equipped to handle complex data relationships and extract meaningful insights from your database. Join operations are a fundamental concept in SQL that allow you to combine rows from two or more tables based on a common column. This process is essential for retrieving data that spans multiple tables, as it enables you to link related information that has been stored separately for efficiency and organization. By using joins, you can create complex queries that pull together data from different parts of a database, making it possible to analyze relationships between entities. For instance, if you have a table of customers and a table of orders A join can help you see which customers have placed orders and what those orders look like. This capability is at the heart of relational database systems, which rely on structured data relationships to maintain consistency and reduce redundancy. The purpose of joins is to combine data from different tables into a single result set, allowing you to access information that would otherwise be scattered across multiple tables. This is particularly useful in scenarios where data is stored in separate tables for efficiency, such as in a customer database where customer details and order details are kept in distinct tables. By using joins, you can retrieve related information that is stored separately, ensuring that you have a complete picture of the data without duplicating it. Additionally, joins support the design of relational databases by enforcing data integrity through foreign key relationships. This means that when you join tables, you are essentially following the logical connections that have been established to maintain accurate and consistent data. There are several types of joins in SQL, each serving a specific purpose depending on the data you need to retrieve. The inner join returns only the rows that have matching values in both tables, making it ideal for cases where you want to filter data based on exact matches. The left join, on the other hand, returns all the rows from the left table and includes matching rows from the right table, filling in null values for columns where there are no matches. This is particularly useful for finding records in one table that lack corresponding entries in another. The right join is similar to the left join, but focuses on the right table, returning all its rows and matching rows from the left table. However, the right join is less commonly used because you can often achieve the same result by swapping the order of the tables and using a left join instead. Finally, the full join combines the results of both left and right joins, returning all rows when there is a match in either table. This type of join is valuable for scenarios where you need to see all data from both tables, regardless of whether there are matches. The inner join is one of the most frequently used join types, as it returns only the rows where the join condition is satisfied. This means that if a row in the left table does not have a corresponding match in the right table, it will not appear in the result set. For example, if you are joining a customer's table with an orders table, an inner join would show only customers who have placed at least one order. This makes it a powerful tool for filtering data based on exact matches between tables. The syntax for an inner join is straightforward, using the ON clause to specify the condition that links the two tables. This type of join is particularly useful when you want to ensure that the data you are retrieving is consistent and directly related. By focusing on matching rows, inner joins help eliminate incomplete or irrelevant data, making it easier to work with precise and accurate results. The left join is designed to return all the rows from the left table, even if there are no matching rows in the right table. This is especially useful when you need to ensure that you do not lose any data from the primary table, even if some entries do not have corresponding information in the secondary table. For instance, if you are analyzing customer data and want to see all customers regardless of whether they have placed an order, a left join would include all customers with null values in the columns from the orders table for those who have not made any purchases. This type of join is invaluable for identifying records that might be missing in one table, such as finding customers who have not yet completed a transaction or products that have not been sold. The presence of null values in the result set allows you to easily spot these discrepancies and take further action if needed. The right join is similar to the left join, but focuses on the right table instead of the left. It returns all the rows from the right table and includes matching rows from the left table, with null values for columns where there are no matches. However, the right join is rarely used in practice because its functionality can be replicated by swapping the order of the tables and using a left join instead. For example, if you want to retrieve all orders and their corresponding customer information, a right join on the orders table would achieve the same result as a left join on the customers table. This makes the right join less common, as developers often prefer to maintain a consistent order of tables in their queries. Despite its limited use, the right join remains a valid option in specific scenarios where the right table is the primary focus of the analysis. The full join is unique in that it combines the results of both left and right joins, returning all rows from both tables when there is a match in either. This means that if a row in the left table does not have a corresponding match in the right table, it will still appear in the result set, and vice versa. This type of join is particularly useful for scenarios where you need to see all data from both tables, such as comparing customer data with order data to identify any gaps or overlaps. However, it is important to note that not all SQL dialects support the full join. For example, MySQL does not natively support this operation, requiring developers to use a combination of left and right joins to achieve the same result. Despite these limitations, the full join is a powerful tool for comprehensive data analysis, allowing you to examine relationships between tables in a more holistic manner. In conclusion, joins are an essential component of SQL that enable you to retrieve and analyze data from multiple tables efficiently. Understanding the different types of joins, such as inner, left, right, and full, allows you to choose the most appropriate method based on your specific data requirements. Whether you need to filter data based on exact matches, ensure all records from one table are included, or combine data from both tables, joins provide the flexibility to handle a wide range of scenarios. Practicing with real-world examples, such as joining customer and order data, or analyzing product and sales information, can help reinforce your understanding of how these operations work. By mastering joins, you can unlock the full potential of relational databases and gain deeper insights into the relationships that drive your data. Aggregate functions are essential tools in SQL that allow you to perform calculations across multiple rows of a database table and return a single value. These functions are particularly useful for summarizing large datasets into meaningful insights. For example, you can determine the total number of sales, the average salary of employees, or the highest and lowest values in a specific column. Common aggregate functions include count, which counts the number of rows or non-null values, sum, which adds up numeric values, AVG, which calculates the average of a numeric column, and max and min, which identify the maximum and minimum values in a column. These functions are the foundation for generating reports and analyzing trends in data. The group by clause is a critical component of SQL that organizes rows with similar values into summary groups. This allows you to analyze subsets of data rather than the entire dataset. For instance, if you have sales data spread across different regions, using group by on the region column will enable you to calculate total revenue for each region individually. This is particularly useful when you need to compare performance across different categories or segments. Without group by, you would only get a single summary for the entire dataset, which might not provide actionable insights. Combining group by with aggregate functions like sum or AVG allows you to derive meaningful statistics for each group. The syntax for the group by clause is straightforward, but requires careful structure. The basic format is select column, aggregate function from table group by column. It is important to note that the group by clause must come after the where clause if used, and before the order by clause. For example, if you want to count the number of employees in each department, the query would be select department, count from employees group by department. This ensures that the count is calculated for each unique department value. Paying attention to the order of clauses is crucial to avoid syntax errors and ensure the query returns the intended results. Let's explore the most commonly used aggregate functions in detail. Count is versatile, as it can count all rows in a table using count, or only non-null values in a specific column. Sum adds up numeric values, making it ideal for calculating totals like sales or expenses. AVG computes the average value of a numeric column, which is useful for metrics like average salary or temperature. Max and min identify the highest and lowest values in a column, respectively, which can help in spotting outliers or extremes. Understanding these functions is essential for any data analysis task, as they form the basis for generating insights from raw data. Now let's look at practical examples of how group by can be applied. The first example groups sales data by region to calculate total revenue per region. This helps businesses understand which areas are performing best. The second example calculates the average price of products grouped by their type, which can inform pricing strategies. The third example uses group by along, with having to filter groups with more than 5 tasks assigned to an employee, highlighting high workload scenarios. These examples demonstrate how group by transforms raw data into actionable information by organizing it into meaningful categories. The having clause is used to filter groups based on conditions that involve aggregate functions. Unlike the where clause, which filters rows before aggregation, having operates on the results of the aggregation. For instance, you might want to find departments where the average salary exceeds a certain threshold. The query select department, AVG salary from employees group BY department, having AVG salary 50,000 would return only those departments meeting the condition. This distinction is crucial because having allows you to refine your analysis after summarizing the data, ensuring that your insights are both accurate and relevant. Handling null values in aggregate functions requires careful consideration. Most aggregate functions, such as sum, AVG, max, and min, automatically ignore null values, meaning they do not affect the calculation. However, count includes all rows, even those with nulls in other columns, while count column only counts non-null entries. To manage missing data, functions like coalesce or ifnull can replace nulls with default values. For example, subcoalesce asils. 0 ensures that any missing sales data is treated as 0, preventing inaccurate totals. Properly addressing nulls is vital for maintaining the integrity of your analysis. When working with aggregate functions, following best practices ensures clarity and efficiency. Using aliases such as sum sales as total sales improves readability, especially in complex queries. Avoid including non-aggregated columns in the select clause unless they are part of the group by clause, as this can lead to unexpected results. For example, selecting department and count without grouping by department would cause an error. Additionally, optimizing performance by creating indexes on frequently grouped columns can significantly speed up query execution, especially for large datasets. These practices help maintain clean, efficient, and reliable SQL code. Common errors when using aggregate functions often stem from misunderstandings of their requirements. One frequent mistake is omitting the group by clause when using an aggregate function, which can result in a single summary value for the entire dataset instead of grouped results. Another error is using having without a group by clause, which is invalid because having relies on aggregated data. Lastly, attempting to aggregate non-numeric data, such as applying sum to a text column, will cause a syntax error. Recognizing these pitfalls and understanding their solutions is key to writing effective SQL queries. In summary, aggregate functions and the group by clause are indispensable tools for summarizing and analyzing data. They allow you to transform raw data into actionable insights by organizing it into meaningful groups and performing calculations across multiple rows. The halving clause further refines this analysis by filtering aggregated results, while handling null values ensures accuracy. By mastering these concepts and following best practices, you can efficiently derive valuable insights from complex datasets. Regular practice with real-world examples will solidify your understanding and enhance your ability to leverage SQL for data-driven decision-making. Subqueries, also known as nested queries, are a powerful feature in SQL that allow you to embed one query within another. This approach helps break down complex data retrieval tasks into smaller, more manageable parts. By using subqueries, you can perform filtering, comparisons, and data aggregation in a structured way. For example, you might first calculate an average value and then use that result to filter records in the main query. This capability makes subqueries essential for handling intricate database scenarios. There are 4 main types of subqueries that serve different purposes in SQL. Scalar subqueries return a single value, making them ideal for comparisons or calculations. Row subqueries return a single row with multiple columns, which is useful when you need to compare entire rows of data. Column subqueries produce a single column with multiple rows, often used in clauses, or for filtering based on dynamic lists. Table subqueries return multiple rows and columns, acting as temporary tables for further processing. Understanding these types helps you choose the right approach for your data needs. A scalar subquery is a query that returns exactly one value. For instance, the query select from employees, where salary select AVG salary from employees, uses a scalar subquery to compare each employee's salary with the average salary of the entire table. This type of subquery is particularly useful for conditional filtering, such as identifying records that meet specific criteria based on calculated values. However, it's crucial to ensure that scalar subqueries return a single value to avoid errors that could disrupt the main query's execution. Row subqueries compare a row of values against the result of another query. For example, the query select from customers where name, city equals select name, city from orders, where ordered equals 1001 checks if any customer's name and city match match the details from a specific order. This approach is useful when you need to match multiple columns simultaneously. It's important to note that the number and order of columns in the row must match exactly with the subqueries result to ensure accurate comparisons. Column subqueries return a list of values from a single column, which is often used in clauses or for filtering data based on dynamic lists. For example, the query select from products, where price in select price from inventory retrieves products whose prices exist in the inventory table. This type of subquery is particularly helpful when dealing with data that changes frequently, as it allows you to dynamically reference values without hard-coding them into the main query. Table subqueries return a temporary table that can be used as a derived table in the main query. For instance, the query select from sales, where year equals 2023, as yearless sales creates a temporary table of sales data for 2023, which can then be further processed. This approach is commonly used in join operations, or when you need to simplify complex queries by breaking them into smaller, reusable components. Table subqueries act as a bridge between multiple data sources, enabling more flexible data manipulation. Nested queries involve subqueries within other subqueries, allowing for multi-layered data analysis. For example, the query select from employees, where salary select AVG salary from select salary from employees, where department equals sales as sales salaries first filters salaries by department, calculates the average, and then compares it to individual salaries. This technique is powerful for tackling complex scenarios where data needs to be processed in multiple steps. However, careful planning is required to ensure that nested queries remain readable and efficient. When working with subqueries, following best practices ensures clarity and reliability. Using aliases for subqueries improves readability by giving them meaningful names, especially in complex queries. Avoiding unnecessary nesting simplifies the query structure and reduces the risk of errors. Testing subqueries independently helps verify their accuracy before integrating them into larger queries. These practices not only enhance the quality of your SQL code, but also make it easier to maintain and debug over time. Subqueries are widely used in various real-world scenarios. They can help identify top performers by comparing individual metrics against aggregated values, such as average or maximum. They also enable dynamic comparisons across tables, allowing you to retrieve data that depends on the results of another query. Additionally, subqueries are essential for filtering results based on computed values, such as identifying records that meet specific conditions derived from other data. These use cases highlight their versatility in data analysis and decision-making. In conclusion, subqueries and nested queries significantly enhance the flexibility and power of SQL. They allow you to perform intricate data manipulations that would be difficult or impossible with simple queries. Mastering these techniques enables more efficient analysis and helps uncover insights hidden within complex datasets. By practicing with real-world scenarios, you can strengthen your ability to leverage subqueries effectively, turning them into a valuable tool in your SQL toolkit. Data manipulation language is a critical component of the SQL programming language that allows users to interact with the data stored within database tables. This set of commands enables the addition, modification, and removal of data, making it essential for maintaining and managing database contents. The three primary commands within DML are insert, update, and delete. These commands serve as the foundation for any database operations that involve changing the data itself. Whether you are adding new entries to a table, modifying existing records, or removing outdated information, these commands provide the necessary tools to ensure the database remains accurate and up to date. Understanding how to use these commands effectively is crucial for anyone working with relational databases. The insert command is used to add new records to a table. This is particularly useful when you need to populate a database with initial data or update it with new information. The basic syntax for the insert command is insert into table name followed by a list of columns, and then the corresponding values. For example, inserting a new employee into an employees table might involve specifying the name and salary columns and providing the relevant data. It is important to note that the insert command can be used to add a single row or multiple rows at once, making it a versatile tool for data entry. When using the insert command, it is essential to ensure that the values provided match the data types of the columns being inserted into. This helps prevent errors and ensures the integrity of the database. Additionally, specifying the columns explicitly can help avoid issues if the table structure changes over time. The update command is designed to modify existing records within a table. This is particularly useful when you need to correct information, apply changes to specific entries, or reflect new data in the database. The syntax for the update command involves specifying the table name, followed by the set clause to define the changes, and a where clause to identify the records that need to be updated. For instance, updating an employee's salary would require identifying the specific employee using a unique identifier such as an ID. It is crucial to use the where clause effectively to target only the intended records. Without a properly defined where condition, the update command can inadvertently modify all rows in the table, leading to data corruption. Therefore, always double-check the where clause to ensure it accurately identifies the records you want to update. The delete command is used to remove records from a table, which is necessary when data is no longer needed or needs to be purged for various reasons. The syntax for the delete command involves specifying the table name and a where clause to define the conditions for the records to be deleted. For example, deleting an employee record might involve targeting the specific employee using their ID. It is important to exercise caution when using the delete command because once data is deleted, it is typically not recoverable without a backup. This makes it essential to verify the where clause and ensure that the correct records are being targeted. In some cases, the truncate command can be used as an alternative to delete, but it removes all records from a table and cannot be undone. Always have a backup strategy in place before performing any delete operations. When working with data manipulation commands, following best practices is essential to ensure data accuracy and prevent unintended consequences. One of the most important practices is to back up data before performing bulk updates or deletions. This provides a safety net in case something goes wrong during the operation. Using transactions is another critical practice, as it allows you to group multiple operations together and either commit them all at once or roll them back if an error occurs. This helps maintain the integrity of the database. Additionally, validating the where clauses in update and delete commands is crucial to ensure that only the intended records are affected. Testing queries on small datasets before applying them to larger ones can also help identify potential issues and prevent widespread data loss. By adhering to these best practices, you can minimize risks and ensure that your database remains reliable and consistent. When working with data manipulation commands, several common errors can occur, but they can often be avoided with careful planning and attention to detail. One frequent error is missing the where clause in an update or delete command, which can lead to unintended modifications or deletions of all records in a table. To resolve this, always ensure that the where clause is included and properly defined to target only the specific rows you want to affect. Another common issue is a data type mismatch in an insert command, where the values provided do not match the expected data types of the columns. This can result in errors or incorrect data being stored. To avoid this, verify that the values match the column data types and handle any necessary conversions. Additionally, violating constraints such as primary key or unique constraints can cause insert operations to fail. This often occurs when attempting to insert duplicate values into a column that enforces uniqueness. To address this, check for existing records or constraints before executing the insert command. By being mindful of these potential issues, you can ensure smoother and more reliable database operations. In summary, the insert, update, and delete commands are fundamental tools for managing data within a database. These commands enable users to add, modify, and remove records, making them essential for maintaining accurate and up-to-date data. Proper use of these commands is crucial for ensuring data integrity and preventing errors. By following best practices such as backing up data, using transactions, and validating where clauses, you can minimize risks and avoid unintended data loss. Additionally, understanding common errors and their solutions helps ensure that database operations are performed efficiently and safely. As you continue to work with SQL, mastering these commands will be key to effectively managing and manipulating data in a relational database environment. Data types are the rules that dictate how data is stored and managed within tables in a database. They determine the kind of data a column can hold, such as numbers, text, dates, or special values. Column constraints are like the guidelines that ensure data remains accurate and consistent. For example, constraints can prevent invalid entries or enforce specific conditions. Choosing the right data types and constraints is crucial for designing a database that is efficient, scalable, and easy to maintain. It helps avoid data corruption, ensures data is stored optimally, and supports the logical structure of the information being managed. Numeric data types are used to store numerical values. The integer type handles whole numbers, both positive and negative, such as 100 or -5. Decimal and numeric are designed for precise decimal numbers, making them ideal for financial calculations where accuracy is critical, like 10.5. Float and double store approximate floating point numbers, which are useful for scientific computations where exact precision is less important, such as 3.14159. SMALLINT is a smaller version of integer, suitable for values within a narrower range, such as -32,768 to 32,767. Selecting the appropriate numeric type ensures efficient storage and avoids unnecessary memory usage. String data types handle textual information. Charn stores fixed-length strings, meaning it always uses the specified number of characters, padding with spaces if necessary. For example, SQL in a char 3 column will occupy 3 characters. Varcharn is variable length, using only as much space as needed, like hello in a varchar10 column. Text is used for large volumes of text, such as articles or paragraphs, and does not have a strict length limit. Binary stores binary data, such as images or files, in a format that is not directly readable as text. Each type has its use case, depending on the size and nature of the data. Date and time data types manage temporal information. Date stores calendar dates, such as 2023-10-15. Time holds time values, like 1430-00. DATETIME and timestamp combine both date and time, often used for tracking events, such as 2023-10-15, 1430-00. Interval is used to represent time durations, such as 2 hours or 3 days. These types are essential for applications that require tracking timestamps, scheduling, or calculating time differences. Proper use ensures accurate temporal data handling and supports queries based on time ranges. Special data types serve unique purposes. Boolean stores true or false values, often represented as 1 or 0. UUID generates universally unique identifiers, ensuring no duplicates across systems, such as 550 E80 400E29B, 41D4 A716 4466 554 40000. JSON stores structured data in a key value format, allowing for flexible data storage like name, John. Geometry handles spatial data such as points or polygons used in geographic information systems. These types expand the capabilities of databases to handle complex and specialized data requirements. The primary key constraint is a fundamental tool for uniquely identifying each row in a table. It ensures that no two rows have the same value in the primary key column, and it also enforces the not null and unique constraints. This makes it ideal for the main identifier of a table, such as userid in a user's table. By establishing a primary key, you create a reliable way to reference and retrieve specific records, which is essential for relationships between tables and efficient data management. The foreign key constraint maintains referential integrity between tables. It ensures that the value in a column matches a value in another table's primary key, preventing orphaned records. For example, a custom rid in an orders table must exist in the customer's table. This constraint is vital for maintaining consistency across related data, reducing errors, and ensuring that relationships between tables remain valid. It acts as a safeguard against invalid data entries that could disrupt the database's structure. The unique constraint ensures that all values in a column are distinct. Unlike primary key, it allows null values, but only one null is permitted per column. This is useful for fields like email addresses or usernames, where duplicates are not allowed. By applying unique, you prevent accidental duplication and maintain data accuracy. However, it is important to note that a column with a unique constraint can still have one null value, which is a key distinction from primary key. The not null constraint guarantees that a column cannot have missing or blank values. This is critical for fields that must always contain data, such as a user's name or date of birth. By enforcing not null, you ensure that essential information is always present, reducing the risk of incomplete or unreliable data. This constraint is often used in conjunction with other constraints to create a robust data model that adheres to specific business rules. The default constraint provides a fallback value for a column if no value is specified during insertion. This simplifies data entry by automatically populating the column with a predefined value, such as active for a status field. Default can also use functions like currentTimestamp to automatically record the current date and time. This reduces the need for manual input and ensures consistency, especially for fields that require standard values or dynamic data. The check constraint enforces specific conditions on column values, ensuring they meet certain criteria. For example, a check age equals 18 ensures that only users aged 18 or older can be added. It can also restrict values to a specific set, like gender in M. F. This constraint is powerful for validating data at the time of insertion or update, preventing invalid entries and maintaining data quality. However, some databases may have limitations on the complexity of conditions allowed in check constraints. Best practices for data types and constraints involve careful planning and consideration. Choose the smallest data type that can accommodate your data to optimize storage and performance. Use constraints to enforce business rules, such as ensuring a customer exists before an order is placed. Avoid unnecessary nulls by using not null where appropriate, as this ensures critical data is always present. Finally, document your choices to make the database easier to understand and maintain for future users or developers. Data types define the structure and storage requirements of data, while column constraints ensure accuracy and reliability. Together, they form the foundation of a well-designed database. Properly selecting data types and constraints improves performance by reducing redundancy and optimizing storage. It also enhances maintainability by making the database easier to manage and scale. By following best practices, you can create databases that are robust, efficient, and capable of supporting complex applications and growing data needs. Database tables serve as the foundational structure for organizing and storing data in relational databases. They act as containers for rows and columns, where each row represents a unique record, and each column defines a specific attribute of that record. Structuring data properly is essential for efficient storage, quick retrieval, and maintaining data integrity. By defining clear table structures, we ensure that data is stored logically, reducing redundancy and enabling seamless queries. The primary objectives of this section include mastering the skills to create, modify, and manage tables effectively, which are critical steps in building robust database systems. To begin working with databases, we use the create table statement to define the structure of a new table. This command allows us to specify the table name and the columns it will contain, along with their corresponding data types. The syntax for this command is straightforward, requiring the table name followed by a list of column definitions. For example, the statement create table employees id int name varchar 50 creates a table named employees with two columns, one for integer values and another for variable length strings with a maximum of 50 characters. This foundational step ensures that data is stored in a consistent and predictable format. When defining table columns, choosing the appropriate data types is crucial. Common data types include integers for numerical values, variable length strings for text, dates for temporal data, Boolean values for true-false conditions, and decimals for precise numeric calculations. Alongside data types, constraints play a vital role in enforcing rules on the data. Constraints such as primary key ensure that each record has a unique identifier. Not null prevents empty values. Unique guarantees no duplicate entries. And foreign key establishes relationships between tables. For instance, the constraint id int primary key not null ensures that the id column contains unique, non-empty values, providing a reliable way to reference records. Once a table is created, it may need adjustments to accommodate evolving requirements. The alter table command allows us to modify the structure of an existing table. This can involve adding new columns to expand the table's capabilities, modifying existing columns to change their data types, or even deleting columns that are no longer needed. For example, the command alter table table name add column name data type introduces a new column to the table. Similarly, alter table table name modify column name new data type updates the data type of an existing column. These modifications ensure that the table remains aligned with the needs of the database and its users. When tables are no longer needed, two commands can be used to remove them: drop and truncate. The drop table command permanently deletes the entire table, including its structure and all stored data. This action is irreversible and should be used with extreme caution. In contrast, the truncate table command removes all the data within a table while preserving its structure, allowing the table to be reused without redefining its columns. Both commands are powerful tools, but they carry significant risks. It is essential to verify the impact of these actions and ensure that data is backed up before execution. Establishing relationships between tables is a core aspect of relational database design. This is achieved through foreign key constraints, which link data in one table to another. For example, a department ID in an employee's table can reference the ID column in a department's table, ensuring that every employee is associated with a valid department. These relationships enforce referential integrity, preventing inconsistencies such as orphaned records. By carefully defining foreign keys, we maintain the accuracy and reliability of data across interconnected tables, which is vital for complex database systems. In summary, tables are the building blocks of any relational database, providing a structured way to store and manage data. Understanding how to create, modify, and manage tables is essential for effective database design and maintenance. Commands like create, alter, drop, and truncate are powerful tools that enable these operations, but they must be used judiciously. As you continue to explore SQL, practicing these concepts through real-world scenarios will reinforce your ability to design efficient and scalable database solutions. Always prioritize careful planning and data integrity when working with tables. Indexes are a fundamental tool in SQL programming that significantly enhance the speed of data retrieval operations. Imagine a library where books are organized by title, author, or subject. This is similar to how indexes work in a database. By creating an index on a specific column, the database can quickly locate the required data without scanning the entire table, which is known as a full table scan. This is especially crucial for large data sets where efficiency is paramount. However, there is a trade-off. While indexes make reading data faster, they can slow down writing operations such as inserts, updates, and deletes. This is because the database must maintain the index structure whenever data changes, which adds overhead. Therefore, it is essential to use indexes judiciously to balance performance gains and operational costs. There are several types of indexes, each serving a unique purpose. A clustered index determines the physical order of data in a table, much like how a book is organized by chapters. Since a table can have only one clustered index, it is typically created on the primary key or a column that is frequently accessed. A non-clustered index, on the other hand, is a separate structure that contains a copy of the indexed columns, along with pointers to the actual data rows. This allows for multiple non-clustered indexes on a single table, which can be beneficial for complex queries. Lastly, composite indexes combine two or more columns to optimize queries that involve multiple conditions. For example, an index on both customer ID and order date can accelerate searches for specific orders. Understanding these index types helps in designing efficient database structures tailored to specific application needs. Deciding when to use indexes requires careful consideration of query patterns and data characteristics. Columns that are frequently used in where clauses, join conditions, or order by statements are prime candidates for indexing. For instance, if a query often filters data by a customer's email address, an index on that column can drastically reduce retrieval time. High selectivity columns, such as unique identifiers like primary keys, also benefit from indexing because they narrow down results efficiently. Additionally, indexes on columns that are queried frequently in large tables can prevent performance bottlenecks. However, it is important to avoid indexing columns with low selectivity, such as gender or status, as these may not provide meaningful performance improvements. By aligning indexes with query requirements, you can maximize their effectiveness. Best practices for indexing involve a balance between performance and maintenance. Over-indexing can lead to unnecessary overhead, as each index requires additional storage and processing power. It is crucial to evaluate the necessity of each index and remove those that are rarely used. A covering index, which includes all the columns needed for a query, can eliminate the need to access the underlying table data, further improving performance. For example, if a query selects customer name and email, an index that includes both fields can speed up the retrieval process. regular monitoring of index usage and fragmentation is also vital. As data grows and changes, indexes may become fragmented, leading to slower performance. Rebuilding or reorganizing indexes periodically helps maintain their efficiency. By adhering to these practices, you can ensure indexes remain a valuable asset to your database. Optimizing indexes involves analyzing how queries interact with the database and leveraging tools to refine their effectiveness. Query execution plans provide insights into how the database processes a query, highlighting potential bottlenecks such as full table scans or inefficient joins. By examining these plans, you can identify which indexes are being used and where improvements are needed. Database tools like SQL Server Profiler or the explain command in PostgreSQL allow you to trace and evaluate index usage in real time. Additionally, index compression can be a powerful technique for large datasets, reducing storage requirements while maintaining query performance. However, compression may increase CPU usage, so it is important to weigh the trade-offs. These techniques empower you to make data-driven decisions when optimizing your database's indexing strategy. Despite their benefits, indexes can lead to pitfalls if not managed properly. One common mistake is indexing low selectivity columns, such as gender or status, where the number of distinct values is minimal. In such cases, the index may not provide significant performance gains, making it a waste of resources. Another oversight is neglecting index maintenance, such as fragmentation caused by frequent data modifications. Over time, fragmented indexes can degrade performance, requiring regular rebuilding or reorganization. Additionally, some queries may not benefit from indexes, particularly those that retrieve a large portion of the data or involve complex conditions. For example, a query that filters on a column with many duplicate values may not use an index effectively. Recognizing these pitfalls helps avoid unnecessary complications and ensures indexes are used where they matter most. In conclusion, indexing is a critical component of SQL performance optimization. By strategically placing indexes, you can reduce query latency, improve scalability, and enhance the overall user experience. However, the benefits of indexing are not automatic. They require thoughtful planning, continuous monitoring, and adaptation to evolving data patterns. As databases grow and query demands change, maintaining a balance between read and right operations becomes increasingly important. With the right approach, indexes can transform a sluggish database into a high-performing system, ensuring it meets the needs of modern applications. Remember, the goal is not to index everything, but to index wisely, making every index a valuable asset to your database infrastructure. A primary key is a fundamental concept in relational databases that ensures every record within a table is uniquely identifiable. This uniqueness is crucial because it prevents duplicate entries and allows for precise data manipulation. A foreign key, on the other hand, acts as a bridge between two tables, creating a relationship that maintains consistency across the database. Together, these keys are the backbone of database integrity, ensuring that data remains accurate and logically connected. Without them, databases would struggle with redundancy, inconsistencies, and errors in data retrieval. A primary key serves as the unique identifier for each row in a table. This means no two rows can share the same primary key value, which eliminates ambiguity when referencing specific records. Importantly, primary keys cannot contain null values because nulls represent missing or undefined data, which would compromise the uniqueness requirement. While a primary key can be a single column, such as a customer ID, it can also be a composite key made up of multiple columns. For example, a table tracking inventory might use a combination of product ID and warehouse location as a composite key to ensure uniqueness. A foreign key is a field in one table that links to the primary key in another table, creating a relationship that enforces referential integrity. This relationship ensures that any data entered into the foreign key column must exist in the referenced primary key column. For instance, if a table stores order details, the customer ID in that table must correspond to an existing customer in the customers table. This mechanism prevents orphaned records and maintains the logical flow of data. Additionally, foreign keys restrict actions that could disrupt relationships, such as deleting a customer who still has active orders. Primary keys play a vital role in ensuring data accuracy by providing a reliable way to locate and retrieve specific records. They also enhance performance because databases often use primary keys to index data, making queries faster. Foreign keys, meanwhile, maintain consistency across related tables by ensuring that relationships remain valid. For example, if a customer's information is updated, all related orders must reflect this change to avoid discrepancies. Together, primary and foreign keys form the foundation of relational databases, enabling complex queries and supporting the structured organization of data. Let's take the customer's table as an example. The customer ID column serves as the primary key, acting as a unique identifier for each customer. This ensures that every entry in the table is distinct and can be referenced reliably. For instance, when inserting a new customer, the database requires a unique customer ID. If someone attempts to add a duplicate, the system will reject the insertion. This strict enforcement of uniqueness is critical for maintaining data integrity. The example provided demonstrates how the primary key allows precise data management, ensuring that each customer's information is stored and retrieved accurately. In the orders table, the customer ID column functions as a foreign key, linking each order to a specific customer in the customers table. This relationship ensures that every order is associated with a valid customer. For example, when inserting a new order, the customer ID must match an existing entry in the customers table. If not, the database will reject the insertion, preventing inconsistencies. This mechanism is essential for maintaining the integrity of data across tables. By using foreign keys, databases can enforce relationships and ensure that all connected data remains synchronized and accurate. It's important to note that a table can have only one primary key, though this key can consist of multiple columns, known as a composite key. This restriction ensures that there is a single, unambiguous way to identify records. In contrast, a table can have multiple foreign keys, each linking to a different table. For example, an orders table might have foreign keys for customer ID, product ID, and employee ID, each referencing their respective tables. Additionally, foreign keys must match the data type and constraints of the primary key they reference. This alignment ensures that the relationships between tables are valid and that data remains consistent. One common error occurs when inserting a foreign key value that does not exist in the referenced primary key column. For instance, if an order's customer ID does not match any existing customer, the database will reject the insertion. To avoid this, developers often validate data before insertion or use cascading actions cascading updates and deletes can automatically adjust related records when a primary key is modified or removed. For example, if a customer is deleted with the ON delete cascade option, all related orders would also be deleted. Alternatively, on delete restrict prevents the deletion of a primary key record if it has dependent foreign key entries, ensuring data consistency. Best practices for using primary and foreign keys include using surrogate keys, such as auto-incremented IDs, which are stable and independent of business data. Surrogate keys simplify relationships and reduce the risk of changes affecting existing data. Additionally, foreign keys should be properly indexed to improve query performance, especially when joining tables. Regular validation of relationships is also essential to catch inconsistencies early. By following these practices, developers can ensure that databases remain efficient, scalable, and reliable, supporting complex operations without compromising data integrity. In summary, primary keys uniquely identify records within a table, while foreign keys establish connections between tables. These two concepts work together to ensure data integrity, prevent inconsistencies, and enable efficient querying. Mastering primary and foreign keys is essential for designing robust relational databases, as they form the basis of structured data management. Whether building simple or complex systems, understanding these principles allows for the creation of reliable, scalable, and maintainable database solutions. Views and materialized views are powerful tools in SQL programming that help manage and optimize database interactions. A view is essentially a virtual table created by a saved SQL query. It does not store data itself, but dynamically retrieves it from the underlying base tables whenever it is accessed. Materialized views take this concept further by storing the results of a query as a physical table. This means they hold pre-computed data that can be refreshed periodically. Both views and materialized views serve important purposes. They can improve performance by reducing the need to repeatedly execute complex queries. They also simplify complex queries by allowing users to work with a more straightforward structure. Additionally, they enhance security by restricting access to specific columns or rows, ensuring sensitive data is not exposed unnecessarily. A view is a saved SQL query that functions like a table. Unlike physical tables, views do not store data. Instead, they act as a lens through which you can see the data from one or more base tables. Every time you query a view, the database dynamically executes the underlying SQL statement to retrieve the latest data. This makes views incredibly useful for simplifying complex queries. For example, if you frequently need to join multiple tables or apply specific filters, a view can encapsulate that logic so you don't have to rewrite the same query repeatedly. Views are also ideal for restricting access to certain parts of a database. By defining a view that includes only specific columns or rows, you can control what data users can see. This is particularly valuable in scenarios where you want to protect sensitive information while still providing access to relevant data. The benefits of views extend beyond just simplifying queries. One of the key advantages is that they encapsulate complex logic, making it reusable across different parts of an application or database. This not only saves time, but also reduces the risk of errors that can occur when writing the same logic multiple times. Views also improve the readability and maintainability of SQL code. By abstracting the details of underlying tables and queries, they make the code base easier to understand and manage. Additionally, views provide a layer of abstraction for sensitive data, ensuring that users interact with a curated subset of the database rather than the raw data itself. This abstraction is especially useful in environments where data security is a priority. Furthermore, views can be used in joins, subqueries, and other operations, making them a versatile tool in SQL programming. Creating a view in SQL is straightforward. The basic syntax is to use the create view statement followed by the view name and an as clause that defines the query. For example, the statement create view high sales as select producted sales amount from sales, where sales amount 1000 creates a view named high sales that includes only sales records with amounts exceeding 1000. This view acts as a shortcut for users who need to access this specific subset of data without writing the same query repeatedly. It's important to note that views are read-only by default. This means you cannot directly insert, update, or delete data through a view unless the database system allows it explicitly. However, This read-only nature ensures that the underlying data remains consistent and protected from unintended modifications. While views offer many advantages, they also have limitations that users should be aware of. One common restriction is that certain clauses like order by or distinct may not be allowed in some database systems when creating a view. This can be a challenge when trying to sort results or eliminate duplicates directly in the view definition. Additionally, the performance of a view depends entirely on the underlying query. If the base tables are large or the query is complex, the view may not provide significant performance gains. Another limitation is that updates to the base tables require the view to recalculate its results. This can lead to inefficiencies if the view is used frequently. Finally, views are not well suited for large data sets that change often. Since they do not store data, they may not provide the performance benefits needed for such scenarios. Materialized views take the concept of a view a step further by storing the results of a query as a physical table. Unlike regular views, which dynamically fetch data, materialized views pre-compute and store the results. This means they hold actual data that can be accessed quickly without recalculating the query each time. The data in a materialized view is typically refreshed periodically, either manually or automatically, to ensure it stays up to date. This makes materialized views ideal for scenarios where complex queries are executed frequently. By pre-computing the results, they reduce the load on the source database and improve query performance. They are particularly useful for storing aggregated or summarized data, such as sales totals by region or customer statistics. This pre-computed data can then be used for reporting, analytics, or other operations that require fast access to summarized information. The benefits of materialized views are significant, especially in environments where performance is critical. One of the main advantages is that they drastically improve query performance for repetitive or resource-heavy queries. Since the data is pre-computed and stored, queries against a materialized view can execute much faster than querying the underlying tables directly. This is especially beneficial for large datasets or complex joins that would otherwise take a long time to process. Materialized views also reduce the load on the source database by caching the results of expensive queries. This can help prevent performance bottlenecks and ensure smoother operations. Additionally, they support offline analysis and reporting, allowing users to work with a snapshot of the data without affecting the live database. Finally, materialized views can be indexed, further optimizing their performance and making them a powerful tool for data management. Creating a materialized view follows a syntax similar to creating a regular view, but with the addition of the materialized keyword. The basic structure is create materialized view MV name as select columns from table where condition. For example, the statement create materialized view sales summary as select region, SUM sales amount as total sales from sales group BY region creates a materialized view that stores the total sales per region. This view is not automatically updated when the underlying data changes. Instead, it requires a manual or scheduled refresh to ensure the data remains current. This approach is ideal for scenarios where the data does not change frequently, such as daily or weekly summaries. By storing the results of the query, materialized views provide a balance between performance and data accuracy, making them a valuable tool for data analysis and reporting. Refreshing a materialized view is essential to ensure the data remains accurate. There are two primary methods for refreshing: manual and automatic. A manual refresh is initiated using the refresh materialized view statement, which updates the view's data immediately. This is useful when you need the latest data for a specific task, such as generating a report. Automatic refresh, on the other hand, is configured through database settings or triggers, allowing the materialized view to update at predefined intervals. This is ideal for data that changes regularly, but doesn't require real-time updates. However, there is a trade-off between data freshness and performance. Frequent refreshes can consume resources and impact system performance, while infrequent refreshes may lead to stale data. Choosing the right refresh strategy depends on the specific requirements of the application and the frequency of data changes. The key difference between views and materialized views lies in how they handle data. Views are dynamic and do not store data. They retrieve the latest data from the underlying tables every time they are accessed, ensuring real-time accuracy. This makes them ideal for scenarios where up-to-the-minute data is critical. Materialized views, on the other hand, store the results of a query as a physical table. This means they contain static data that must be refreshed manually or automatically. They are best suited for situations where performance is a priority, such as complex queries or large datasets that are queried frequently. When deciding between the two, consider the need for real-time data versus the benefits of pre-computed results. Views are excellent for encapsulating complex logic and simplifying queries, while materialized views are ideal for optimizing performance and reducing the load on the database. Understanding these distinctions will help you choose the right tool for your specific use case. Good day. Today, we will explore advanced sorting and filtering techniques in SQL, which are essential for refining data retrieval and enhancing query efficiency. These methods allow us to manipulate and organize large datasets with precision, ensuring that the results we extract are both accurate and optimized. By mastering these concepts, you will be able to handle complex data scenarios, improve performance, and make your queries more dynamic. The topics we will cover include sorting with multiple columns, advanced where clauses, subqueries, and critical performance considerations. Let's begin by diving into the intricacies of advanced sorting techniques. Sorting in SQL goes beyond simple alphabetical or numerical order. The order by clause can be used with multiple columns to create hierarchical sorting, such as first sorting by department and then by employee name. Additionally, we can sort by computed values, like the length of a name or the sum of two columns, which adds flexibility in organizing data. In PostgreSQL, handling null values becomes straightforward with the NULLS first or NULLS last options, ensuring that missing data does not disrupt the sorting order. Another powerful approach is using case statements to define custom sorting logic, such as prioritizing certain values over others. These techniques empower you to tailor sorting behavior to specific business needs. Filtering data with the where clause is fundamental, but its true potential lies in combining conditions. Using logical operators like and, or, and not, we can create intricate filters that narrow down results precisely. The between operator simplifies range-based filtering, such as selecting records between specific dates or numbers. The like and ILIKE operators allow pattern matching, with ILIKE offering case-insensitive searches, which is particularly useful in user-facing applications. The IN and not in clauses enable comparisons against multiple values, streamlining queries that would otherwise require repeated OR conditions. These tools collectively enhance the ability to extract relevant data efficiently. Subqueries in the where clause add a layer of dynamism to filtering, allowing values to be determined at runtime. For instance, a subquery might fetch a list of employee IDs to filter records based on current data. Correlated subqueries take this further by referencing columns from the outer query, enabling row-by-row comparisons. The EXISDS and not EXISDS operators provide a way to check for the existence of related records, often outperforming in or not in certain scenarios. However, subqueries can impact performance if not optimized, so techniques like rewriting them as joins or ensuring proper indexing are crucial to avoid bottlenecks. Conditional logic elevates filtering by introducing flexibility. The case statement can be used in where clauses to apply custom conditions, such as filtering based on specific categories or thresholds. In PostgreSQL, the filter clause allows for conditional aggregation, like counting only rows that meet certain criteria. Combining case with order by enables dynamic sorting based on runtime values, such as sorting by a status field with varying priorities. Functions like coalesce and NULLIF help manage edge cases, ensuring that null values do not disrupt calculations or comparisons. These methods make queries more adaptive to complex data scenarios. Performance considerations are vital when working with advanced queries. Indexing the right columns can drastically reduce query execution time, but over-indexing may lead to overhead. Selective filters, such as those using precise conditions, help avoid full table scans, which are resource-intensive. The explain command reveals how the database engine processes queries, offering insights into potential optimizations. Balancing complexity with readability ensures that queries remain maintainable while delivering efficient results. By analyzing execution plans and refining logic, we can achieve a harmonious blend of performance and clarity. To summarize, we have explored advanced sorting techniques, including multi-column sorting, computed values, and null handling. We have enhanced filtering skills through subqueries, case statements, and complex conditions. By addressing performance through indexing and execution plans, we have learned to optimize queries effectively. These techniques are indispensable for real-world data retrieval, enabling you to handle large datasets with confidence and precision. As you continue your SQL journey, remember that practice and analysis are key to mastering these advanced concepts. Common table expressions, often abbreviated as CTEs, are temporary result sets that exist only during the execution of a query. They are defined using the with clause, which allows you to create a named query that can be referenced multiple times within the same statement. This feature is particularly useful when you need to reuse a subquery in different parts of your main query. CTEs enhance the readability and maintainability of your SQL code by breaking down complex queries into smaller, more manageable parts. For example, if you have a query that involves multiple nested subqueries, a CTE can simplify the structure by giving a meaningful name to each logical section. This not only makes the query easier to understand, but also facilitates debugging and future modifications. The basic syntax of a CTE involves the with clause followed by the name of the CTE and the query that defines it. The structure is straightforward, with CTE name as query select from CTE name. This allows you to create a temporary table-like structure that exists only for the duration of the query. CTEs can be nested, meaning one CTE can reference another, or they can be recursive, enabling the processing of hierarchical data. For instance, a recursive CTE can traverse a tree structure, such as an organizational hierarchy, by repeatedly joining the CTE with itself. Additionally, CTEs are not limited to select statements. They can be used with insert, update, and delete operations. This versatility makes them a powerful tool for managing complex database interactions. One of the primary benefits of using CTEs is their ability to simplify complex queries. By dividing a large query into smaller, logically separated components, you can focus on one part at a time, reducing the cognitive load when writing or debugging code. Another significant advantage is their support for recursive queries, which is essential for handling hierarchical data. For example, if you need to retrieve all employees under a specific manager, a recursive CTE can efficiently traverse the hierarchy. Additionally, CTEs can improve performance in certain scenarios by allowing the database engine to optimize the execution plan. While this is not always guaranteed, the structured approach of CTEs often leads to more efficient query execution. However, it is important to note that the actual performance gains depend on the database system and the specific query structure. Let me illustrate a simple CTE with an example. Imagine you have a sales table that records sales transactions. To generate a summary of total sales per salesperson, you can use a CTE. The query would start with the with clause, defining a CTE called sales summary. Inside the parentheses, you write a select statement that groups the sales data by salesperson and calculates the sum of sales. Once the CTE is defined, the main query selects all the results from the CTE. This approach makes the query more organized, as the logic for summarizing the data is encapsulated within the CTE. Additionally, if you need to reference this summary in multiple parts of your query, the CTE provides a reusable component, eliminating the need to repeat the same subquery multiple times. Recursive CTEs are specifically designed for handling hierarchical data, such as organizational charts or bill of materials. A recursive CTE consists of two parts: the initial query and the recursive query. The initial query retrieves the root nodes of the hierarchy, such as the top-level manager in an organization. The recursive query then joins the CTE with the underlying table to retrieve subsequent levels of the hierarchy. For example, in an employees table, the initial query might select managers with no parent, and the recursive part joins employees with their managers using a foreign key relationship. This process continues until all levels of the hierarchy are retrieved. Recursive CTEs are particularly useful in scenarios where the depth of the hierarchy is unknown, as they can dynamically expand to include all relevant records. However, it is important to set a maximum recursion limit to avoid infinite loops in cases where the data might have unexpected structures. When using CTEs, it is essential to follow best practices to ensure clarity and efficiency. First, use CTEs for complex or nested queries where they can provide significant structural benefits. Avoid overusing CTEs for simple subqueries, as this can lead to unnecessary complexity. For instance, if a subquery is only used once, a direct subquery might be more straightforward. Second, name your CTEs clearly to reflect their purpose. Descriptive names make it easier for others and yourself to understand the query's logic. For example, instead of naming a CTE temp, use sales summary to indicate its function. Finally, consider the scope and structure of your queries to ensure that CTEs are used appropriately. By adhering to these guidelines, you can leverage the full potential of CTEs while maintaining readable and maintainable code. In conclusion, CTEs are a powerful feature in SQL that can significantly enhance the structure and clarity of your queries. They allow you to break down complex logic into manageable components, making your code more readable and easier to maintain. Their support for recursion enables the efficient handling of hierarchical data, which is crucial in many real-world applications. By mastering CTEs, you can tackle intricate database scenarios with greater confidence and precision. As you continue to explore SQL, remember that practice and experimentation are key to fully understanding and applying these concepts. With time, you will find that CTEs become an indispensable part of your SQL toolkit, helping you write cleaner, more efficient, and more maintainable code. Window functions are a powerful tool in SQL that allow you to perform calculations across a set of rows that are related to the current row. Unlike traditional aggregate functions, which collapse multiple rows into a single result, window functions maintain the individual row details while still applying calculations. This makes them ideal for scenarios where you need to analyze data in context, such as ranking, cumulative sums, or comparisons within specific groups. For example, you might use a window function to rank sales performance within each region, while still seeing the individual sales figures for each employee. These functions are particularly useful in analytical queries, where the goal is to uncover deeper insights from structured data. By leveraging window functions, you can avoid complex subqueries and joins, making your queries more efficient and easier to understand. The syntax for window functions follows a specific structure that defines the scope of the calculation. At its core, the function is enclosed in parentheses and followed by the over clause, which determines the window of rows to consider. The over clause can include optional components such as partition by, order by, and rows or range to refine the window. The partition by clause divides the dataset into partitions, allowing calculations to be performed independently within each group. The order by clause specifies the order of rows within each partition, which is crucial for functions like ranking or cumulative sums. The ROWS, or range, clauses further define the frame of the window, such as including all rows from the start of the partition up to the current row. This flexibility allows you to combine multiple window functions in a single query, enabling complex analyses without repeating code. There are several common window functions that serve different analytical purposes. The ROWNUMBER function assigns a unique sequential number to each row within a partition, which is useful for creating rankings or identifying specific positions. The rank function also assigns ranks, but leaves gaps when there are ties, meaning the next rank will skip the number of tied rows. In contrast, DENSERANK assigns ranks without gaps, making it suitable for scenarios where consecutive numbers are needed. The NTILE function divides rows into a specified number of buckets, which can be helpful for percentile analysis or grouping data into equal parts. Additionally, the lead and lag functions allow you to access values from previous or next rows within the same partition, enabling comparisons across time or sequences. These functions are essential for tasks like identifying trends, calculating moving averages, or analyzing data over time. The partition by and order by clauses are fundamental to defining how window functions operate. The partition by clause divides the dataset into logical partitions, such as grouping data by department or region, so that calculations are performed independently within each group. This is particularly useful when you need to analyze subsets of data separately. The order by clause then determines the sequence of rows within each partition, which is critical for functions that rely on ordering, such as ranking or cumulative sums. For instance, if you partition by department and order by salary in descending order, you can rank employees within each department based on their earnings. Combining these clauses allows for granular analysis, enabling you to explore patterns and relationships within specific subsets of your data. This level of control makes window functions a versatile tool for handling complex analytical requirements. Analytic queries leverage window functions to perform advanced data analysis that would otherwise require complex subqueries or joins. These queries are designed to compute running totals, moving averages, and percentiles, among other metrics, directly within the main query. For example, a running total can be calculated by summing values values from the start of a partition up to the current row, providing a cumulative view of data over time. Similarly, moving averages can be computed by averaging a fixed number of preceding or following rows, which is useful for smoothing out fluctuations in time series data. By using window functions, you can avoid the overhead of subqueries and joins, resulting in more efficient and readable code. This approach not only simplifies complex logic, but also enhances performance by reducing the need for repeated computations. Window functions have a wide range of practical applications across various domains. One common use case is ranking sales performance within regions, where each salesperson's data is analyzed relative to their peers. Another example is calculating cumulative revenue over time, which helps track financial growth or trends. Identifying top-end records per group, such as the top 5 products in each category, is another scenario where window functions shine. Additionally, comparing current row values with previous or next rows can highlight changes or anomalies, such as detecting sudden drops in sales. For instance, the sum function with a window defined by partition, by region, and order by date can compute a running total of sales for each region over time. These examples demonstrate how window functions can transform raw data into actionable insights, making them indispensable for data-driven decision-making. Mastering window functions is essential for advanced SQL analysis, as they provide the flexibility to handle complex queries efficiently. The key components to focus on are the partition by, order by, and the specific function types, each of which plays a critical role in shaping the results. By understanding how these elements interact, you can design queries that deliver precise and meaningful insights. Analytic queries powered by window functions enable deeper exploration of structured data, uncovering patterns and relationships that might otherwise go unnoticed. Whether you are analyzing sales trends, optimizing business processes, or conducting statistical analysis, window functions offer a powerful and efficient way to achieve your goals. As you continue to practice and experiment with these functions, you will unlock new possibilities for transforming data into valuable information. Null values in SQL represent missing or unknown data and play a critical role in how we handle incomplete information within databases. Unlike zero or an empty string, null is not a value itself, but a marker for absence. This distinction is vital because comparisons involving null often yield unexpected results. Conditional logic, on the other hand, allows us to make decisions within queries, enabling dynamic data processing. By the end of this presentation, you will understand how to manage null values effectively and leverage conditional statements to manipulate and analyze data with precision. In SQL, null is used to indicate that a value is unknown or not present. For example, if a customer's phone number is not provided, the database might store null in that field. It is important to note that null is not a value, which means it cannot be compared using standard operators like equals or not equals. For instance, a query checking for null with equals will not return the expected results. Instead, comparisons involving null typically return an unknown state, which can lead to logical errors if not handled properly. This behavior is unique to SQL and differs from other programming languages where missing values might be treated as zero or empty strings. To work with null values, we use specific operators like isNull and isNotNull. These allow us to explicitly check for the presence or absence of data. For example, a query might filter records where a column is null to identify incomplete entries. Additionally, functions such as coalesce can replace null values with a default, ensuring that calculations or displays do not fail. The nullif function is another tool that returns null if two expressions are equal, which can be useful for avoiding division by zero or other invalid operations. It is crucial to avoid using equals or equals when checking for null, as these operators will not work as intended and can lead to incorrect results. Conditional logic in SQL is implemented through case expressions, which allow us to perform conditional evaluations within queries. A simple case statement compares a single expression to multiple values, making it ideal for straightforward categorizations. For example, a query might use a simple case to assign a status based on a numeric score. A searched case, however, uses Boolean expressions to evaluate complex conditions, offering greater flexibility. This type of case is useful when multiple criteria need to be checked. In MySQL, the if function provides a more concise way to handle basic conditional checks, returning one value if a condition is true and another if it is false. These tools empower us to create dynamic and responsive intensive queries. Let's explore practical examples of how conditional logic works. In one scenario, a case statement can categorize data into labels like high, medium, or low based on specific thresholds. For instance, a sales table might use a case to classify sales amounts into these categories. Another example involves combining conditions with and, or, and not in where clauses to filter data precisely. For example, a query might retrieve records where a customer's status is active and their last purchase was within the last month. The if function can also be used to return different values based on a condition, such as applying a discount if a customer's membership is premium. These examples demonstrate how conditional logic enhances query flexibility and precision to ensure robust handling of null values, and conditional logic follow these best practices. Always use is null or is not null to check for missing data, as other operators will not work correctly. Functions like coalesce help replace nulls with default values, preventing errors in calculations. When constructing conditions, use and, or, and not judiciously to avoid unintended results, and test your queries thoroughly. Additionally, documenting your logic makes it easier for others to understand and maintain your work. By adhering to these guidelines, you can create more reliable and efficient SQL queries that handle edge cases with confidence. In summary, null values require careful handling to prevent errors and ensure accurate results. Conditional logic allows us to make decisions within queries, enabling dynamic data processing. Mastering these concepts is essential for writing reliable and efficient SQL code. As you practice using case, if, and null functions in real-world scenarios, you will gain the skills needed to tackle complex data challenges. Remember, the key to success lies in understanding how nulls behave and how to structure conditions to achieve the desired outcomes. Welcome to this session on advanced join scenarios in SQL. Let us begin by revisiting the foundational concepts of joins. Inner joins allow us to retrieve records that have matching values in both tables, while left joins ensure we retain all records from the left table, even if there are no matches in the right table. Right joins function similarly, but prioritize the right table, and full joins combine the results of both left and right joins to include all records from both tables. understanding these basic join types is essential. But as data relationships grow in complexity, mastering advanced join techniques becomes critical. Today's session will explore self-joins, multi-table joins, and strategies to optimize performance. These skills will empower you to tackle intricate data challenges and extract meaningful insights from relational databases. A self-join is a technique where a table is joined with itself, often using aliases to distinguish between the two instances of the same table. This approach is particularly useful for handling hierarchical data structures, such as employee-manager relationships, where each employee may report to a manager within the same table. For example, consider an employees table with columns like employee-id and manager-id. By joining the table on these columns, we can retrieve both the employee and their manager's details. The syntax for a self-join typically involves specifying the table twice with different aliases, as in select E1 name, E2 name from employees E1, employees E2. This method allows us to compare or relate rows within the same table efficiently. Let us now examine practical examples of self-joins. The first scenario involves identifying employees and their respective managers. By joining the employees table on the manager-id column, we can create a hierarchical view of the organization. For instance, if an employee's manager-id corresponds to another employee's employee-id, the query will link their names. Another use case is comparing sales data across different time periods. Imagine a sales table with a date column. By joining the same table on date ranges, we can analyze trends like month-over-month growth. However, self-joins require careful handling. Without proper filtering conditions, they can result in infinite loops or excessive data duplication. Always ensure that your join conditions include clear constraints, such as E1 employee-id, E2 employee-id, to avoid unintended results. Advanced join scenarios often involve combining multiple tables with complex conditions. For instance, you might need to link a customer's table with an orders table and a products table to retrieve detailed transaction data. Subqueries can further enhance this process by dynamically filtering which rows are included in the join. For example, a subquery might identify the top-selling products, and the join would then focus on those specific entries. Additionally, integrating aggregate functions like count or sum with joins allows for powerful data analysis. Imagine calculating total sales per region by joining sales data with region information and applying a sum function on the sales amount. These techniques enable you to transform raw data into actionable insights. In this section, we will explore several types of advanced joins. The full outer join is designed to combine all records from both tables, ensuring that no data is excluded. This is particularly useful when you need to identify unmatched rows in either table. The cross join, on the other hand, produces a Cartesian product, which means every row from the first table is paired with every row from the second table. While this can be useful for generating combinations, it must be used cautiously due to its potential to create extremely large result sets. The natural join automatically matches columns with the same names between two tables, simplifying the syntax. However, this can lead to unexpected results if column names are not carefully managed. Each of these join types serves a specific purpose and should be selected based on the data requirements of your query. Optimizing join performance is crucial for efficient query execution. One key strategy is indexing the columns used in join conditions. Indexes significantly reduce the time required to locate matching rows, especially in large datasets. Additionally, avoid including unnecessary joins in your queries, as they can complicate the execution plan and slow down the process. For example, if you only need data from two tables, joining a third table that is not essential can degrade performance. Another vital tool is the explain plan command, which provides insights into how the database engine processes your query. By analyzing the execution plan, you can identify bottlenecks such as full table scans and refine your query structure for better efficiency. As we delve into common pitfalls, let us address issues that often arise during join operations. Duplicate column names can cause confusion when joining tables, so using aliases to explicitly reference columns is essential. For instance, if two tables have a column named id, qualifying it with the table name or alias ensures clarity. Incorrect join conditions, such as joining on the wrong column or omitting necessary filters, can lead to inaccurate results. Always verify that your conditions correctly reflect the relationship between tables. Lastly, handling null values in outer joins requires careful consideration. Since outer joins include unmatched rows, nulls may appear in the result set. Techniques like using coalesce or conditional logic can help manage these scenarios effectively. To illustrate the application of advanced joins, let us consider a real-world case study. Imagine analyzing customer orders and shipment data. The orders table might include customer IDs, order dates, and product details, while the shipments table could track delivery statuses and dates. By joining these tables with the customer's table, we can retrieve comprehensive information about each order, such as customer names and shipment timelines. This multi-table approach allows for deeper analysis, such as identifying which customers have the highest order frequencies or tracking delays in shipments. The outcome of this integration is a streamlined process for generating business insights, enabling data-driven decisions that improve operational efficiency and customer satisfaction. In conclusion, mastering self-joins and advanced join techniques is a vital step in becoming proficient in SQL. These skills allow you to navigate complex data relationships and derive meaningful insights from structured data. To solidify your understanding, practice with real-world data sets, experimenting with different join types and optimization strategies. Always prioritize clarity in your queries, ensuring that your join conditions and aliases are well documented. Additionally, focus on performance by leveraging indexes and analyzing execution plans. By combining these practices, you will not only enhance your ability to retrieve data, but also contribute to more efficient and effective database solutions. Stored procedures are pre-written SQL code that resides within the database itself. This means they are stored in the database, allowing multiple applications to access and use them without needing to rewrite the same SQL commands repeatedly. By encapsulating complex logic, stored procedures act as a single point of execution for tasks that might otherwise require lengthy or repetitive code. This not only makes the code more manageable, but also improves performance by reducing the amount of data that needs to be sent over the network. Instead of sending multiple queries from an application to the database, a single call to a stored procedure can handle the entire operation. Additionally, stored procedures enhance security by allowing database administrators to control access through permissions, ensuring that users interact with the database only through predefined, secure pathways. The benefits of using stored procedures are numerous and significant. One of the primary advantages is the ability to centralize business logic, which ensures consistency across different parts of an application. When business rules are defined in a single location, it minimizes the risk of errors and discrepancies that can arise from duplicating code in multiple places. This also reduces code redundancy, as developers can reuse the same stored procedures across various applications, saving time and effort. Security is another key benefit, as stored procedures can be granted specific permissions, limiting direct access to sensitive tables or data. Furthermore, stored procedures often execute faster because they are precompiled by the database engine. This means the database optimizes the code ahead of time, reducing the overhead of parsing and compiling each query when it is executed. The syntax for creating a stored procedure is straightforward and follows a consistent structure. The first line begins with the keyword create procedure, followed by the name of the procedure. The as keyword then introduces the body of the procedure. Within the body, the begin and end keywords define the scope of the procedure, enclosing the SQL statements that make up its functionality. These statements can include select, insert, update, delete, or any other valid SQL commands. It is important to note that the exact syntax may vary slightly depending on the specific database system being used, such as Microsoft SQL Server, Oracle, or PostgreSQL. But the general structure remains similar. Proper formatting and indentation are essential for readability, especially when procedures become more complex. Let me walk through an example of creating a simple stored procedure. Consider the following code. Create procedure get customer data as select from customers. This procedure, named get customer data, retrieves all records from the customers table. By storing this query as a procedure, it can be executed multiple times without rewriting the SQL code, making it more efficient and easier to maintain. Stored procedures can also accept parameters, allowing them to perform dynamic operations. For instance, a procedure might take a customer ID as input and return only the data for that specific customer. This flexibility makes stored procedures powerful tools for handling a wide range of database tasks. To execute a stored procedure, you use the exec or execute command depending on the database system. For example, the command exec get customer data would run the get customer data procedure we discussed earlier. If the procedure has parameters, you can pass them directly in the call. For instance, if a procedure requires a customer ID, you would write exec get customer by id at customer id equals 123. This approach simplifies application code by abstracting the complexity of SQL queries, allowing developers to focus on higher level logic. By centralizing the database interactions, stored procedures also make it easier to update or modify the logic without changing the application code. Stored procedures can accept parameters to make them more versatile. Input parameters allow the procedure to receive data from the caller, enabling dynamic behavior. For example, a procedure might take an integer value representing a customer ID and use it to filter the results. The syntax for an input parameter is at param name data type, where data type specifies the type of data expected. Output parameters, on the other hand, allow the procedure to return values to the caller. These are declared with the output keyword, such as at param name data type output. Here is an example. Create procedure get customer by id at customer id int as select from customers where id equals at customer id. This procedure accepts a customer ID as input and returns all matching records. Parameters make stored procedures adaptable to different scenarios, enhancing their usefulness in real-world applications. When working with stored procedures, following best practices ensures that your code is efficient, maintainable, and secure. First, always use meaningful names that clearly describe the purpose of the procedure. For example, get customer data is more descriptive than proc1. Including comments within the procedure helps other developers understand the logic, especially for complex operations. Avoid making procedures too complex by breaking them into smaller, focused tasks. This improves readability and reduces the risk of errors. Finally, thoroughly test each procedure before deploying it to production. Testing ensures that the procedure behaves as expected under various conditions and helps identify potential issues early. These practices contribute to a more reliable and scalable database environment. In summary, stored procedures are a powerful feature of SQL that streamline database operations. They enhance security by controlling access, improve performance through pre-compilation, and make code more maintainable by centralizing logic. Mastering the creation and execution of stored procedures is essential for anyone looking to advance their SQL skills. As you continue your training, I encourage you to practice writing and testing procedures in real-world scenarios. This hands-on experience will deepen your understanding and help you leverage stored procedures effectively in your projects. Functions in SQL are reusable code blocks that perform specific tasks, allowing developers to encapsulate logic and reuse it across multiple queries. This approach not only streamlines the coding process, but also enhances code efficiency, readability, and maintainability. By centralizing functionality, functions reduce redundancy and make it easier to update or debug code. Common use cases include data manipulation, such as transforming values or formatting dates, performing calculations like mathematical operations or string manipulations, and optimizing queries by abstracting complex logic into manageable units. These functions act as building blocks that empower developers to write cleaner, more organized SQL scripts. The syntax for creating a function in SQL typically begins with the create function statement, followed by the function name, parameters, and return type. For example, the function add numbers takes two integer parameters and returns an integer. The body of the function, enclosed in delimiters, contains the logic to be executed, such as adding the two values and returning the result. Functions can be written in various languages, including SQL itself, PL/PG/SQL for PostgreSQL, or other procedural languages, depending on the database system. This flexibility allows developers to choose the most appropriate language for the task at hand, whether it involves simple calculations or complex business logic. SQL functions are categorized into three main types: scalar, aggregate, and table-valued functions. Scalar functions operate on a single value and return a single result, such as converting text to uppercase with the upper function or rounding numbers with round. Aggregate functions, on the other hand, process a set of values and return a single summary result, like calculating the sum of a column with sum or the average with AVG. Table-valued functions return a table as their output, enabling them to be used in queries like regular tables. For instance, a function that generates a list of dates can be called in a select statement to retrieve dynamic data. Each type serves distinct purposes, making functions versatile tools for data processing. Functions can be seamlessly integrated into SQL queries, enhancing their flexibility and power. Developers can call functions directly in select, where, or join clauses to perform specific operations. For example, a function that retrieves an employee's name based on an ID can be used in a select statement to fetch names from an employee's table. Functions also allow combining with operators and other SQL clauses to create complex logic. Imagine using a function to calculate a discount rate within a where condition, or joining results from a table-valued function with another table. This integration enables dynamic and reusable query structures, reducing the need for repetitive code. Best practices for writing SQL functions emphasize clarity and reliability. First, functions should focus on a single task to ensure they are easy to understand and maintain. For instance, a function that calculates tax should not also handle data retrieval. Second, parameters should be used to make functions adaptable, allowing them to process different inputs without code changes. Thorough testing is crucial to identify edge cases or errors, ensuring the function behaves as expected in all scenarios. Finally, documentation is essential to explain the function's purpose, parameters, and any assumptions, making it easier for others to use and modify. These practices collectively improve the quality and usability of SQL functions. SQL functions are widely used in real-world scenarios to automate tasks and enforce consistency. They can automate repetitive calculations, such as applying tax rates or calculating discounts, which reduces manual effort and minimizes errors. Encapsulating business logic within functions ensures that rules are applied uniformly across the database, preventing discrepancies. For example, a function that validates data formats can be reused in multiple queries. Additionally, functions improve query performance by reducing redundancy, as complex logic is centralized rather than repeated in multiple places. This optimization leads to faster execution and more maintainable code. In conclusion, functions are essential for modular and efficient SQL programming, offering a structured way to handle complex tasks. Mastering their creation and usage expands the capabilities of SQL queries, enabling developers to tackle advanced data processing challenges. By practicing the design, implementation, and debugging of functions, learners can strengthen their skills and apply them effectively in real-world projects. The ability to write and utilize functions not only enhances productivity, but also fosters a deeper understanding of SQL's capabilities, making it a valuable skill for any database professional. Triggers are specialized database objects designed to automatically execute a set of predefined actions when specific events occur within the database. These events typically include data manipulation language operations, such as inserting, updating, or deleting records in a table or view. The primary purpose of triggers is to automate routine or complex database tasks, eliminating the need for manual intervention. By being tied directly to the structure of tables or views, triggers ensure that certain actions are consistently applied whenever the associated event is triggered. This automation helps maintain data integrity, enforce business rules, and streamline database operations without requiring external programs or user input. There are three main types of triggers that determine when their actions are executed relative to the triggering event. The first type is the after trigger, which runs after a data manipulation language operation, such as an insert, update, or delete. These are commonly used for tasks like logging changes or updating related tables. The second type is the before trigger, which executes before the actual data modification occurs. This is useful for validating data or modifying values before they are committed to the database. The third type, the instead of trigger, is unique because it replaces the default action of a data manipulation language operation. This is particularly valuable when working with views, where direct modifications to the underlying tables may not be feasible. Each trigger type serves a distinct purpose, allowing developers to tailor their database behavior precisely to their needs. The syntax for creating a trigger in SQL follows a structured format that specifies the trigger's name, the event that activates it, the table or view it is associated with, and the actions it performs. The basic structure begins with the create trigger statement, followed by the trigger name. Next, the trigger type after before or instead of is specified, indicating when the trigger should execute relative to the event. The ON clause identifies the table or view that the trigger is linked to. The for each row clause ensures the trigger operates on individual rows rather than the entire table, which is crucial for row-level processing. Finally, the trigger's logic is enclosed within the begin and end keywords, forming a block of code that executes when the trigger is activated. Understanding this syntax is essential for effectively implementing and managing triggers in a database environment. Triggers are incredibly versatile tools for addressing a wide range of database automation needs. One common use case is data validation, where triggers can enforce business rules that cannot be easily implemented through standard constraints. For example, a trigger might check if a new order's quantity exceeds available stock before allowing the insertion. Another critical application is logging changes to a history table, which helps track modifications for auditing or debugging purposes. Triggers can also be used to synchronize data across multiple tables or even databases, ensuring consistency in complex systems. Additionally, they can enforce constraints that are too intricate for foreign keys, such as maintaining relationships based on dynamic conditions. These use cases highlight the role of triggers in enhancing database functionality and reliability. Let's examine an example of a trigger that updates inventory levels automatically when a new order is placed. The trigger is named Updates to After Order and is set to execute after an insert operation on the orders table. The for each row clause ensures the trigger processes each row individually, which is vital for accurate inventory adjustments. Inside the trigger body, the update statement modifies the inventory table by reducing the quantity of the product associated with the new order. The new keyword references the values of the newly inserted row, allowing the trigger to access the product ID and quantity from the orders table. This example demonstrates how triggers can seamlessly integrate with other database objects to maintain data consistency without requiring manual updates. Triggers are particularly effective for automating repetitive or time-sensitive database tasks. For instance, they can automatically update timestamp columns whenever a record is modified, ensuring that the most recent activity is always recorded. This is useful for tracking when data was last changed, which is critical for audit trails. Another common application is archiving old records, where triggers can move data to a separate table or archive database when it meets specific criteria, such as being older than a certain date. Triggers can also be used to send notifications, such as inserting a message into a notification table or triggering an email alert when a significant event occurs. These automated actions reduce the burden on database administrators and ensure that critical processes are handled consistently and efficiently. While triggers offer powerful capabilities, their use requires careful consideration to avoid potential pitfalls. One key best practice is to avoid embedding overly complex logic within triggers, as this can lead to performance degradation and make the database harder to maintain. It is essential to thoroughly test triggers in various scenarios to ensure they behave as expected and do not introduce unintended side effects, such as infinite loops or conflicts with other database objects. Documentation is also crucial, as it helps other developers understand the purpose and functionality of each trigger. Finally, triggers should be used to automate database-level tasks rather than replacing application logic, ensuring that the separation of concerns between the database and application layers remains clear and manageable. In summary, triggers are a fundamental feature of SQL databases that enable automation, enhance data integrity, and reduce the need for manual intervention. By executing automatically in response to specific events, they provide a robust mechanism for enforcing business rules, maintaining consistency, and streamlining operations. However, their effectiveness depends on careful design, rigorous testing, and adherence to best practices. When implemented correctly, triggers can significantly improve the reliability and efficiency of database systems, making them an invaluable tool for developers and database administrators alike. Normalization is the process of organizing data within a database to reduce redundancy and improve data integrity. By structuring data in a logical and efficient manner, we ensure that information is stored consistently and can be accessed without unnecessary duplication. This approach helps prevent data inconsistencies and makes it easier to manage large datasets. The key concept behind normalization is to eliminate duplicate data and ensure that dependencies between data elements are consistent, which ultimately leads to a more reliable and scalable database system. The purpose of normalization is to address several critical challenges in database design. First, it minimizes data redundancy by ensuring that each piece of information is stored in only one place, which reduces the risk of conflicting data. Second, it enhances data integrity by organizing data logically, making it easier to enforce rules and constraints. Third, normalization simplifies the database structure, which streamlines maintenance and updates. Finally, it helps reduce anomalies that can occur during data insertion, update, or deletion operations, ensuring that changes to the database do not lead to errors or inconsistencies. The benefits of normalization are significant for both database performance and management. By eliminating redundant data, normalization optimizes storage and improves retrieval efficiency, which can lead to faster query execution. It also makes databases easier to manage and scale as they grow, since changes can be made in a structured and controlled manner. Consistent data across tables ensures that information remains accurate and up-to-date, which is crucial for reliable reporting and analysis. Additionally, normalization reduces the risk of data corruption or inconsistencies, providing a more robust foundation for applications that depend on the database. First, normal form, or 1NF, is the foundational step in normalization. It requires that all values in a table are atomic, meaning they cannot be further divided. This means no repeating groups or multi-valued fields within a single column. For example, if a table stores multiple phone numbers for a single contact, those should be split into separate rows rather than being stored in a single cell. Each row in the table must also be unique, which is achieved by assigning a primary key. This ensures that every record can be distinctly identified and accessed. Second, normal form, or 2NF, builds on 1NF by addressing partial dependencies. A partial dependency occurs when a non-key attribute depends on only part of a composite primary key. To achieve 2NF, all non-key attributes must depend on the entire primary key. For instance, consider a table with a composite key of student ID and course ID. If the course name depends only on the course ID, it should be moved to a separate table to eliminate the partial dependency. This step ensures that data is organized in a way that avoids unnecessary duplication and maintains logical consistency. Third, normal form, or 3NF, extends 2NF by by removing transitive dependencies. A transitive dependency occurs when a non-key attribute depends on another non-key attribute rather than the primary key. For example, if a table contains a customer ID, customer name, and customer address, and the address depends on the customer ID, but the city within the address depends on the address itself, this creates a transitive dependency. To resolve this, the city should be moved to a separate table. This ensures that all non-key attributes depend directly on the primary key, further enhancing data integrity and reducing redundancy. Boyce-Codd normal form, or BCNF, is a more stringent version of 3NF that addresses certain anomalies that may still exist in 3NF. BCNF requires that every determinant in a table is a candidate key, meaning that no non-trivial functional dependencies exist unless the determinant is a superkey. This ensures that there are no overlapping candidate keys that could lead to inconsistencies. For example, if a table has two candidate keys that overlap, BCNF would require splitting the table to eliminate dependencies that do not conform to this rule. This form provides an additional layer of protection against data anomalies and ensures a more robust database structure. The normal forms provide a structured approach to database design, each building on the previous one. First normal form ensures atomic values and eliminates repeating groups, while second normal form removes partial dependencies by ensuring all non-key attributes depend on the entire primary key. Third normal form goes further by eliminating transitive dependencies, and Boyce-Codd normal form strengthens this by ensuring that all determinants are candidate keys. Together, these forms create a systematic framework for designing databases that are efficient, consistent, and easy to maintain. In conclusion, normalization is a critical technique for creating structured, efficient, and consistent databases. By following the principles of each normal form, we can minimize redundancy, improve data integrity, and ensure that databases are scalable and maintainable. Applying these concepts during the design phase helps prevent common issues that arise from poorly structured data, making it easier to manage and query information over time. As you work with SQL databases, remember that thoughtful normalization lays the foundation for reliable and high-performance data systems. Good day. Today, we will explore the concept of denormalization in SQL programming. Denormalization involves restructuring database tables to combine data into fewer tables, which can significantly improve query performance by reducing the need for complex joins. However, this approach comes with trade-offs that we must carefully evaluate. By the end of this session, you will understand what denormalization is, analyze its benefits and risks, and learn how to make informed decisions about when and how to apply it in real-world scenarios. Denormalization is a technique where we merge multiple tables into a single structure to minimize the number of joins required during data retrieval. This process introduces redundancy, meaning the same data is stored in multiple places, but it allows for faster access to information. For instance, in data warehousing, where large volumes of data are queried frequently, denormalization helps reduce the time spent on joining tables. It is also commonly used in read-heavy applications, such as reporting systems, where quick data retrieval is critical. To fully grasp denormalization, it's essential to compare it with normalization. Normalization is the process of organizing data to eliminate redundancy and ensure data integrity by splitting tables into smaller, related structures. This approach prioritizes data accuracy and reduces anomalies. In contrast, denormalization sacrifices some redundancy to improve performance and simplify query execution. The key trade-off lies in balancing the complexity of a highly normalized database with the performance gains of a denormalized one. Understanding this balance is crucial for effective database design. There are several compelling reasons to consider denormalization. One primary goal is to enhance query performance by reducing the number of joins, which can be computationally expensive. For example, in analytical environments, joining multiple tables to generate a report can slow down the process. Denormalization simplifies this by consolidating data into a single table. Additionally, it streamlines complex queries, making them easier to manage and optimize. It is particularly useful for read-heavy workloads, such as dashboards or data analytics, where frequent reads outweigh the need for frequent updates. The performance benefits of denormalization are substantial. By minimizing joins, we reduce the amount of data that needs to be processed during queries, which speeds up retrieval. This also lowers I/O operations as the database engine accesses fewer tables. Furthermore, denormalized structures often allow for more efficient indexing and caching strategies, which can further improve performance. These advantages make denormalization a powerful tool for handling large datasets, especially in scenarios where scalability is a priority. However, denormalization introduces data redundancy, which increases storage requirements. Storing the same data in multiple locations can lead to higher disk usage and potential inefficiencies. More critically, it raises the risk of data inconsistency if updates are not carefully managed. For example, if a customer's address is stored in multiple tables and only one is updated, the data becomes fragmented. This highlights the need for robust design practices to mitigate the risks associated with redundancy, while leveraging the benefits of faster queries. One of the most significant challenges of denormalization is the potential for update anomalies. When data is duplicated across tables, ensuring all instances are updated correctly becomes complex. For instance, if a customer's address is updated in one table, but not others, the data becomes inconsistent. This requires meticulous maintenance to synchronize changes across all relevant tables. The effort required to maintain consistency can offset some of the performance gains, making it essential to weigh the trade-offs carefully before implementing denormalization. Let's look at some practical examples of denormalization. A common approach is to merge customer and order tables into a single view, which eliminates the need to join them during queries. This is particularly useful in reporting tools that require quick access to customer transaction data. Another example is storing pre-computed aggregates, such as total sales per region, to avoid recalculating these values during each query. Additionally, embedding lookup values directly into transaction tables, like product categories, can simplify queries and reduce the need for joins. These strategies demonstrate how denormalization can be applied to specific use cases. Denormalization is most effective in certain scenarios. It is ideal for read-heavy applications, such as dashboards or analytics platforms, where the primary goal is to retrieve data quickly. In high-latency environments, where every millisecond counts, denormalization can provide a critical performance boost. Legacy systems with existing performance bottlenecks may also benefit from this approach. Furthermore, when joins are too costly due to the size or complexity of the dataset, denormalization offers a viable solution. However, it is not a one-size-fits-all strategy and must be applied thoughtfully. To implement denormalization effectively, follow these best practices. First, denormalize selectively rather than universally, focusing on areas where the performance gains are most impactful. Document all redundant data and establish clear rules for updates to prevent inconsistencies. Use triggers or application logic to automate data synchronization, ensuring that changes are propagated consistently. Finally, continuously monitor the system after implementation to assess performance and data integrity, making adjustments as needed. These steps help mitigate risks while maximizing the benefits of denormalization. In conclusion, denormalization is a powerful technique that balances performance and complexity. It is not a universal solution, but a strategic choice that depends on specific use cases. While it can significantly improve query speed and simplify data access, it requires careful evaluation of trade-offs, particularly regarding data integrity and maintenance. By prioritizing thoughtful design and ongoing monitoring, you can leverage denormalization to enhance performance without compromising long-term maintainability. Always consider the unique needs of your application before deciding to adopt this approach. Securing databases is a critical aspect of any data management strategy. Without proper security measures, unauthorized individuals can access, alter, or even destroy sensitive information. This not only risks the integrity of the data, but also compromises confidentiality and availability. Data integrity ensures that the information remains accurate and consistent over its entire life cycle. Confidentiality protects data from being accessed by unauthorized users, while availability guarantees that authorized users can access the data when needed. User permissions play a central role in this process by defining what actions each user can perform within the database. By carefully managing these permissions, organizations can mitigate risks and ensure that only the right people have access to the right data. Understanding the distinction between authentication and authorization is essential for effective database security. Authentication authentication is the process of verifying a user's identity, typically through a username and password. This step ensures that the person attempting to access the system is who they claim to be. Once authentication is successful, authorization comes into play, determining what specific actions the user is allowed to perform. For example, a user might be authenticated, but only authorized to view certain data. Separating these two processes allows for a more robust security framework, where roles are defined to control access to resources. This separation ensures that even if one layer is compromised, the other can still act as a safeguard. User roles and groups are fundamental to simplifying permission management. Instead of assigning individual privileges to each user, organizations can define roles such as admin, developer, or guest. These roles encapsulate a set of permissions that align with specific job functions. By assigning roles to users, administrators can efficiently manage access without the need to configure permissions for every individual. This approach not only streamlines maintenance, but also reduces the likelihood of human error. For instance, a developer role might include permissions to create and modify tables, while a guest role might be limited to reading data. This structured approach ensures consistency and clarity in access control. Granting and revoking permissions is a core function of SQL security. The grant command allows administrators to provide specific privileges to users or roles. For example, granting select access enables a user to retrieve data, while insert allows them to add new records. Conversely, the revoke command is used to remove these permissions when they are no longer needed. This dynamic control ensures that users have access only for as long as it is necessary. An example of this is the command grant select on table to user, which explicitly defines the scope of access. By mastering these commands, administrators can maintain a secure and flexible database environment. SQL privileges are categorized into 3 main types, each serving a distinct purpose. Data level privileges include actions like select, insert, update, and delete, which govern how users interact with the data itself. Schema level privileges, such as create, alter, and drop, control the structure of the database, allowing users to add or modify tables and other objects. Administrative privileges, like super or grant option, provide high-level control over the database system. These privileges can be assigned at different levels, such as the database, table, or even column level, offering granular control over access. This layered approach ensures that security measures are both comprehensive and precise. Creating a user with specific permissions involves a series of SQL commands that define access rights. The create user command establishes a new user account, often requiring a password for authentication. For example, the command create user user at localhost, identified by password, sets up a user with a specified password. Following this, the grant command assigns permissions, such as select and insert, to the user for a specific database. Finally, the flush privileges command ensures that these changes are immediately applied. This process demonstrates how SQL allows for precise control over who can access and modify data, reinforcing the importance of careful configuration. Adhering to security best practices is vital for maintaining a secure SQL environment. Strong, unique passwords for each user are the first line of defense against unauthorized access. Regularly auditing and reviewing user permissions helps identify and rectify any discrepancies or outdated access rights. Additionally, the principle of least privilege should guide all permission assignments, ensuring that users have only the access necessary to perform their tasks. These practices collectively reduce the risk of data breaches and ensure that the database remains resilient against potential threats. In conclusion, securing SQL environments is essential to prevent data breaches and misuse. By implementing robust authentication and authorization mechanisms, organizations can ensure that only authorized users have access to sensitive information. Proper user management fosters accountability and control, making it easier to track and manage database activities. Prioritizing security during the design and maintenance of databases not only protects data, but also builds trust with stakeholders. As technology evolves, so too must our commitment to safeguarding the integrity of our data. Good day. Today, we will explore advanced query optimization, a critical practice for enhancing the performance of SQL queries. Advanced query optimization involves analyzing and refining the way databases execute queries to ensure they run as efficiently as possible. This is especially vital in large-scale databases, where even small inefficiencies can lead to significant delays and resource consumption. By focusing on reducing execution time, minimizing resource usage, such as CPU and memory, and improving scalability, we can ensure that our databases handle high volumes of data and user requests seamlessly. These objectives not only improve user experience, but also reduce operational costs and support future growth. Let's begin by understanding how execution plans can help us visualize and analyze query processing. Execution plans provide a detailed roadmap of how a database engine processes a query. They break down the steps involved, such as table scans, joins, and sorting, allowing us to identify potential bottlenecks. Tools like Explain in PostgreSQL or the execution plan feature in SQL Server offer insights into these steps. For instance, Explain in PostgreSQL displays the query plan in a structured format, while SQL Server's execution plan shows a graphical representation. When analyzing these plans, key metrics to focus on include the cost, which estimates the relative effort required for each step, and the difference between scan and seek operations. A scan reads all rows in a table, while a seek uses an index to locate specific rows efficiently. Additionally, the type of join used, such as hash joins or merge joins, can significantly impact performance. Understanding these elements helps us make informed decisions to optimize queries. Index optimization is a cornerstone of efficient SQL performance. By strategically using indexed columns in WHERE, join, and order by clauses, we can drastically reduce the time it takes to retrieve data. For example, an index on a frequently filtered column in a where clause allows the database to quickly locate the relevant rows. However, it's important to avoid over-indexing, as each additional index increases right overhead and consumes more storage. Over-indexing can also slow down insert, update, and delete operations. Instead, we should leverage composite indexes for multi-column queries. A composite index on 2 or more columns can be more effective than individual indexes, especially when queries filter on multiple columns simultaneously. This approach balances the benefits of indexing with the need for efficient data management. Query rewriting techniques can transform complex queries into more efficient ones. One common strategy is to replace subqueries with joins where possible, as joins often benefit from indexes and can be executed more quickly. For instance, a subquery that retrieves data from a related table might be rewritten as an inner join, allowing the optimizer to choose a more efficient execution plan. Another technique is using common table expressions, CTEs, to simplify complex queries. CTEs improve readability and can sometimes enable the optimizer to reuse intermediate results. Additionally, minimizing nested functions in where clauses is crucial. For example, using a function like upper on an indexed column in a where condition can prevent the database from using the index, leading to slower performance. By restructuring these elements, we can ensure that queries leverage indexes effectively. Avoiding common pitfalls is essential for maintaining optimal query performance. One frequent mistake is applying functions to indexed columns in where conditions. For example, if a column is indexed, but the query uses a function like datpart or convert on that column, the index may not be utilized. This results in a full table scan, which is inefficient. To prevent this, we should structure queries to avoid such functions or consider creating a computed column if necessary. Another pitfall is allowing full table scans by not optimizing join conditions. Ensuring that join columns are indexed and that the conditions are selective can drastically reduce the amount of data processed. Finally, limiting result sets with where clauses instead of filtering after retrieval is critical. Filtering early in the query reduces the volume of data that needs to be transferred and processed, improving overall efficiency. Advanced join optimization involves selecting the most appropriate join type for the data and workload. Inner joins are generally faster than outer joins because they only return matching rows, whereas outer joins must account for non-matching rows. For large datasets, hash joins are often the best choice, as they use memory to create a hash table of one table and then probe the other, making them efficient for unsorted data. Merge joins, on the other hand, require both tables to be sorted, making them ideal for datasets that are already ordered. Regardless of the join type, ensuring that the join columns are indexed and that the database statistics are up to date is crucial. Accurate statistics help the optimizer choose the most efficient plan, avoiding unnecessary resource consumption. Query hints provide a way to influence the optimizer's decisions, but they should be used with caution. Hints like force order, index, or loop join can override the default execution plan, which might be beneficial in specific scenarios. For example, forcing a particular join order or using a specific index can resolve performance issues when the optimizer's default choice is suboptimal. However, relying too heavily on hints can lead to brittle queries that may degrade as data or statistics change. It's essential to test the impact of hints in environments that closely mimic production, ensuring that they deliver the expected performance gains without introducing new problems. Always document the rationale for using hints to maintain clarity for future maintenance. Partitioning and indexing work together to enhance query performance for large tables. Partitioning divides a table into smaller, more manageable pieces based on a specific criterion, such as a range of values or a hash of the data. This allows queries to focus on relevant partitions rather than scanning the entire table. For example, a table partitioned by date can quickly retrieve data from a specific time period. Combining partitioning with indexing further improves efficiency, as indexes can be created on individual partitions. However, maintaining partitioned tables requires careful management, such as updating statistics and reorganizing partitions to prevent fragmentation. This approach ensures that queries remain fast and scalable as data grows over time. Analyzing performance metrics is key to identifying and addressing inefficiencies in queries. Monitoring query execution time helps us understand how long a query takes to complete, while tracking resource consumption such as CPU and I/O usage reveals bottlenecks. Tools like Explain Analyze in PostgreSQL or SQL Profiler in SQL Server provide detailed insights into how queries are executed, including the time spent on each step. By correlating query patterns with database workload trends, we can identify recurring issues and optimize queries that frequently impact performance. For example, a query that runs during peak hours might require more aggressive optimization than one that runs during off-peak times. This data-driven approach ensures that our optimizations are targeted and effective. To summarize, advanced query optimization involves a combination of techniques such as analyzing execution plans, using indexes strategically, rewriting queries for efficiency, and leveraging partitioning. These strategies help reduce execution time, minimize resource usage, and improve scalability. However, it's important to balance optimization with maintainability, ensuring that queries remain readable and manageable. Continuous practice and monitoring are essential for sustaining performance gains. As databases evolve and workloads change over time. By applying these principles consistently, we can build robust and efficient SQL solutions that meet the demands of modern applications. Thank you for your attention. Execution plans are visual or textual representations of how a database executes SQL queries. They provide a detailed roadmap of the steps the database engine takes to retrieve or modify data. By examining these plans, you can see the sequence of operations, such as reading from tables, joining data, or sorting results. Understanding execution plans is essential for optimizing query performance because they reveal inefficiencies and help identify areas for improvement. Whether you're working with a simple query or a complex transaction, execution plans serve as a diagnostic tool to ensure your database runs smoothly and efficiently. An execution plan breaks down the operations used to execute a query, such as table scans, joins, and sorts. Each operation represents a specific action the database takes, like scanning an entire table to find matching rows or combining data from multiple tables. The plan includes details about data flow, which shows how information moves between operations, and operator types, which describe the nature of each step. Additionally, execution plans often provide estimated costs, indicating the resources required for each operation, such as CPU usage or disk I/O. These plans can be generated by various database systems, including SQL Server, PostgreSQL, and Oracle, and are available in both text and graphical formats. Execution plans matter because they help identify inefficient operations that can slow down your queries. For example, a full table scan might indicate a lack of proper indexing, while excessive sorting could suggest unoptimized query structures. By analyzing these plans, you can troubleshoot slow queries and pinpoint the root causes of performance issues. They also offer insights into how the query optimizer chooses execution strategies, allowing you to understand why a particular plan was selected. This knowledge empowers you to make informed decisions about query design, indexing, and database configuration to achieve optimal performance. To view execution plans, different database systems offer specific tools. In SQL Server, you can use the Include Actual Execution Plan option in SQL Server Management Studio to see the plan as the query runs. In PostgreSQL, the Explain command provides a textual representation of the plan, while Explain Analyze adds runtime statistics. Oracle users can utilize Explain Plan to generate a plan or access Oracle Enterprise Manager for a graphical view. Most systems allow you to view plans in either text or graphical formats, depending on your preference and the complexity of the query. These tools are invaluable for diagnosing performance issues and refining your SQL code. Key components of an execution plan include operators, cost, data flow, and cardinality. Operators represent the specific actions taken during query execution, such as scanning a table, joining data, or sorting results. Cost estimates the resources required for each operation, helping you identify high-resource steps. Data flow describes how data moves between operators, illustrating the sequence of processing. Cardinality refers to the estimated number of rows processed at each step, which is crucial for understanding how the optimizer predicts the size of intermediate results. Together, these components provide a comprehensive view of how a query is executed and where optimizations might be needed. Common execution plan operators include table scans, index seeks, join types, and sorts. A table scan reads all rows from a table, which can be inefficient for large data sets. An index seek, on the other hand, retrieves specific rows using an index, making it faster for targeted queries. Join types, such as nested loops, hash joins, or merge joins, determine how data from multiple tables is combined. Sort operators order data based on specified columns, which can be resource-intensive if not optimized. Understanding these operators helps you recognize patterns in your execution plans and make adjustments to improve performance. The query optimizer plays a critical role in generating execution plans by selecting the most efficient strategy based on available data. It considers factors like statistics about data distribution, the presence of indexes, the complexity of the query, and resource constraints such as memory and CPU. For instance, if statistics indicate that a table has many duplicate values, the optimizer might choose a different approach than if the data is evenly distributed. Execution plans can also change over time as data evolves or schema modifications occur, making it essential to review plans regularly to ensure they remain optimal for current conditions. Analyzing execution plans for performance involves looking for high-cost operators that may indicate inefficiencies. For example, a full table scan on a large table could signal the need for an index. Inefficient joins, such as nested loops with large datasets, might benefit from alternative join types. Comparing estimated and actual row counts helps identify inaccuracies in the optimizer's predictions, which can lead to suboptimal plans. Tools like query simulators or plan forcing mechanisms allow you to test different scenarios and validate the impact of changes. By systematically evaluating these elements, you can refine your queries and improve overall database performance. Best practices for execution plan analysis include reviewing plans for complex or slow queries to identify potential bottlenecks. Using filtered data helps test specific scenarios without overwhelming the system. Avoid over-optimizing for rare cases, as this can lead to suboptimal performance in common situations. Regularly updating statistics ensures the optimizer has accurate information to make informed decisions. By following these practices, you can maintain efficient query execution and adapt to changing data patterns. Consistent analysis and refinement of execution plans are key to sustaining high performance in dynamic database environments. Execution plans are critical for diagnosing and improving SQL performance. They provide a detailed view of how queries are executed, helping you identify inefficiencies and make targeted optimizations. Understanding their structure and components empowers you to create more efficient queries and make informed decisions about indexing and database design. Regular practice with real-world scenarios enhances your ability to interpret and utilize execution plans effectively. As you continue to work with SQL, mastering execution plan analysis will become an essential skill in your toolkit for maintaining high-performing database systems. Date dates and time intervals are fundamental to organizing and analyzing temporal data in SQL. Whether it's tracking user activity, managing transactions, or monitoring events, understanding how to handle dates and times is essential for accurate data interpretation. SQL offers a robust set of built-in functions to manipulate these values, allowing you to perform operations like extracting specific components, calculating differences, or formatting outputs. Mastering these concepts ensures that you can query and report on time-sensitive data with precision, which is critical in fields like finance, logistics, and real-time analytics. Let's explore some of the most commonly used date functions in SQL. The currentDate function returns the current date without the time component, making it ideal for scenarios where you only need the day, month, and year. The now function, or currentTimestamp, provides both the date and time, which is useful for logging events with exact timestamps. The date function extracts the date portion from a data time value, helping to isolate the date part when dealing with combined date and time data. The extract function allows you to retrieve specific elements such as the year, month, or day from a date. Finally, DATEADD and DATESUB let you add or subtract intervals to dates, enabling dynamic calculations like determining future deadlines or past events. These functions are the building blocks for working with temporal data in SQL. Time intervals in SQL are defined using the interval keyword, which lets you specify durations in units like years, months, days, hours, minutes, or seconds. For example, interval 1 day adds 1 day to a date, while interval 30 minute adds 30 minutes. This feature is particularly useful for calculating future dates, scheduling tasks, or analyzing time-based trends. When you add or subtract an interval to a date, SQL automatically handles the complexities of varying month lengths and leap years. For instance, adding 7 days to October 1st, 2023 results in October 8th, 2023. By leveraging intervals, you can create flexible queries that adapt to different time frames without hard-coding specific dates. Calculating the difference between two dates is a common task in SQL, and functions like DATDIFF, and TIMESTAMPDIFF help achieve this. DATDIFF returns the number of days between two dates, while DATDIFF in PostgreSQL and TIMUSTMPDIFF in MySQL allow for more granular intervals such as hours or minutes. For example, DATEDIFF 2023-1005, 2020-31001 gives a result of 4 days. When working with dates stored as strings, it's crucial to convert them into proper date types using cast or TODATE to ensure accurate calculations. These functions are invaluable for tasks like determining project durations, analyzing customer behavior, or tracking service life cycles. Formatting dates to meet specific requirements is another key aspect of working with temporal data. In MySQL, the DATFORMAT function allows you to customize the output using format patterns like %y for the year, %m for the month, and %d for the day. PostgreSQL uses TOCHAR with similar patterns, such as YYYY for the year and MM for the month. For example, DATEFORMAT 2023-1005, %Y%M%D produces 2023-1005. It's important to avoid relying on default formats, as they can vary between systems or locales. Always specify the desired format to ensure consistency and clarity in your reports or applications. Despite the power of SQL's date and time functions, there are several pitfalls to be aware of. Time zones can introduce inconsistencies, especially when dealing with data from multiple regions. Daylight saving time changes may also cause unexpected results, such as duplicate timestamps or skipped hours. Using date functions incorrectly, like passing invalid inputs or misapplying interval units, can lead to errors or misleading outputs. Additionally, null values in date fields can disrupt calculations if not handled properly. To mitigate these issues, always validate date inputs, account for time zone differences, and implement robust error handling in your queries. Let's look at some practical examples of how these functions can be applied. To calculate a customer's age, you can subtract the year part of their birth date from the current year using extract. For instance, extractyar from currentdat minus extractyar from birth date gives an approximate age. To check if a task is overdue, compare the due date with the current date using a where clause. For project duration, DATEDIFF can calculate the number of days between start and end dates, and dividing by 7 gives the duration in weeks. These examples demonstrate how date and time functions can solve real-world problems and improve data-driven decision-making. In conclusion, mastering dates and time intervals in SQL is essential for effective data analysis and reporting. The built-in functions provide the flexibility to handle complex temporal calculations, from simple date differences to advanced formatting and interval arithmetic. By practicing with real-world scenarios, you can reinforce these concepts and apply them confidently in your work. Always test your queries with edge cases, such as leap years, time zone changes, or invalid date inputs, to ensure reliability. As you continue to explore SQL, remember that a solid understanding of date and time operations will significantly enhance your ability to derive insights from temporal data. Today, we will explore the critical role of string manipulation in SQL and how it empowers data professionals to transform and analyze textual data effectively. String functions and regular expressions are essential tools for tasks such as data cleaning, pattern recognition, and text formatting. By the end of this session, you will gain a solid understanding of key objectives. Mastering string functions like concatenation, substring extraction, and trimming, as well as leveraging regular expressions for advanced pattern matching and data transformation. These skills are vital for handling unstructured data and ensuring consistency in datasets. Let's begin by diving into the foundational string manipulation functions available in SQL. In SQL, string manipulation functions are indispensable for modifying and extracting data from text fields. The concat function allows you to combine multiple strings into a single result, which is particularly useful when merging first and last names or joining segments of a URL. The substring function enables you to extract specific portions of a string, such as isolating a city name from an address or a date from a timestamp. The length function provides the number of characters in a string, which can help validate input or optimize storage. Trim removes unwanted leading or trailing spaces, ensuring data cleanliness. Finally, the replace function substitutes specific characters or substrings, such as standardizing phone numbers by replacing hyphens with dots. Together, these functions form the backbone of text processing in SQL. Regular expressions, or regex, are powerful tools for matching, extracting, and replacing patterns within strings. strings. In SQL, functions like regexpsubstr allow you to extract substrings that match a specific pattern, such as pulling email domains from a list of addresses. The regexpreplac function lets you replace parts of a string based on a regex pattern, which is ideal for sanitizing data or correcting formatting inconsistencies. Lastly, regexplic filters rows by checking if a string matches a given pattern, similar to using where clauses with complex conditions. These functions are particularly valuable when dealing with irregular or semi-structured data, enabling you to perform tasks that would be difficult with basic string functions alone. Let's apply these concepts with practical examples. For instance, extracting email domains requires combining substring with instr to locate the position of the @ symbol, and then isolating the domain part. Validating phone numbers with regexplic involves creating a pattern that matches specific formats, such as XXX, XXXXXXX, or +1 XXX, XXX, XXXX. Cleaning data using replace can remove special characters or standardize entries, such as converting all commas to periods in a numeric field. These examples demonstrate how string functions and regex can solve real-world data challenges, making your queries more efficient and your datasets more reliable. Moving beyond basics, advanced techniques in string manipulation include using wildcards like percent symbols, underscores, and brackets for pattern matching. The percent symbol matches any sequence of characters, while the underscore matches a single character, and brackets define a set of possible characters. Case sensitivity in regex is another critical consideration. For example, adding a flag like I can make matches case insensitive, which is useful when comparing names or addresses. Combining string functions with regex allows for complex operations, such as extracting specific data from unstructured text or transforming multiple fields in a single query. These techniques unlock greater flexibility when working with diverse datasets. To ensure optimal performance and maintainability, follow these best practices. Avoid overusing regex on large datasets, as it can significantly slow down queries. Instead, use it judiciously where it provides the most value. Always test regex patterns in isolation to confirm they work as intended before integrating them into larger queries. Documenting complex string logic such as nested functions or intricate regex patterns, is essential for future reference and collaboration. These practices not only improve query efficiency, but also make your code easier to understand and modify over time. To recap, we've covered essential string manipulation functions, regular expressions, and their applications in real-world scenarios. These tools are fundamental for data cleaning, analysis, and transformation, enabling you to handle text data with precision. As you continue learning, remember that practice is key. Experiment with real data sets to reinforce your understanding. By mastering these techniques, you'll be better equipped to tackle complex data challenges and derive meaningful insights from your data. Thank you for your attention, and I encourage you to explore these concepts further in your own projects. Advanced data aggregation refers to the techniques used to summarize and analyze complex data sets that go beyond simple row-level data. While basic aggregation, such as using group by, allows for grouping data by specific columns and applying functions like sum or count, advanced aggregation enables more nuanced insights. For example, it can handle multi-level summaries where data is grouped across multiple dimensions, such as time, geography, and product categories. It also supports dynamic pivoting, which transforms rows into columns for more flexible data presentation, and provides analytical insights that reveal trends, patterns, and relationships within the data. These techniques are essential for businesses needing to extract actionable information from large, complex datasets. In advanced SQL programming, several functions enhance aggregation capabilities. Grouping SETS allows for custom combinations of groups, enabling precise control over which dimensions to aggregate. ROLLUP and cube are variations that generate hierarchical and all possible combinations summaries, respectively. For instance, ROLLUP can provide totals for regions, then countries within those regions, while cube covers every possible grouping. Window functions like ROWNUMBER, rank, and NTILE add layers of analysis by performing calculations across a set of rows related to the current row. Additionally, statistical functions such as PRCNTILECUNT and APPROXPRCNTIL help analyze data distributions, making them invaluable for tasks like calculating median values or identifying performance thresholds. Grouping sets ROLLUP, and Cube are powerful tools for multidimensional aggregation. Grouping sets is ideal when you need specific groupings, such as aggregating sales data by region and product category, but not by individual cities. ROLLUP, on the other hand, creates hierarchical summaries, like total sales by region, then by country within that region, and finally by city. This is particularly useful for generating reports with nested totals. Cube takes this a step further by generating all possible combinations of groupings, which can be helpful for exploratory analysis, but may result in large data sets. Understanding when to use each method ensures efficient and targeted data analysis. The pivot operator transforms rows into columns, making it easier to compare values across different categories. For example, if you have sales data with product categories as rows, Pivot can convert those categories into columns, allowing you to see sales figures for each category side by side. This is particularly useful for creating cross-tabulated reports. However, Pivot has limitations. It requires predefined column names, making it less flexible for dynamic data. Additionally, queries using Pivot can become complex and harder to maintain if the number of categories changes frequently. Despite these constraints, Pivot remains a valuable tool for static or semi-static datasets. Dynamic pivoting is necessary when the number of categories is unknown or changes frequently. For instance, if you are analyzing sales data for products with varying categories, you cannot hard-code column names in a pivot query. In such cases, using case statements or dynamic SQL allows you to generate column names programmatically. Dynamic SQL involves constructing queries at runtime, which can adapt to new data. Tools like Pivot, combined with UNPIVOT, enable bidirectional transformations, converting columns back into rows when needed. This flexibility is critical for applications requiring real-time data analysis or handling evolving datasets. Let's explore practical examples of these techniques. In a sales report, using ROLLUP can generate totals for regions, countries, and individual products, providing a comprehensive view of performance. For a user activity dashboard, Pivot can transform time-based metrics, such as daily login counts, into columns for easier comparison. Analyzing customer segments with NTILE and rank helps categorize users into percentiles or rankings, enabling targeted marketing strategies. These examples demonstrate how advanced aggregation and pivoting can simplify complex data analysis and support decision-making processes. Optimizing advanced aggregation queries is crucial for performance. Overusing Cube can lead to excessive computation and large result sets, so it's better to use grouping sets when specific groupings are needed. Indexing on columns used in aggregation, such as date or category fields, can significantly speed up query execution. Additionally, using with ROLLUP can improve readability in hierarchical data by automatically including subtotals and totals. Always test queries with real-world datasets to identify bottlenecks and ensure efficiency. These best practices help maintain performance while leveraging the full power of advanced aggregation techniques. In summary, advanced aggregation and pivoting are essential for analyzing complex datasets and extracting meaningful insights. Choosing the right technique, such as pivot for static data or dynamic SQL for evolving datasets, ensures accurate and efficient results. Mastering these concepts requires practice with real-world data, as hands-on experience helps understand their nuances and limitations. By applying these tools strategically, you can transform raw data into actionable intelligence, driving informed decisions and improving business outcomes. Keep experimenting and refining your skills to stay proficient in SQL programming. SQL is the backbone of data-driven decision-making in industries like finance, healthcare, e-commerce, and more. Imagine a world where businesses can't track customer preferences, manage inventory, or analyze trends. That's where SQL comes in. It enables efficient data storage, retrieval, and analysis for business operations, acting as the silent engine behind every transaction, report, and insight. From managing customer relationship systems to optimizing supply chains, SQL is the universal language that connects data to action. Real-world use cases include customer relationship management systems that keep track of interactions, inventory systems that ensure products are always in stock, and data analytics that turn raw numbers into strategic advantages. Without SQL, the data that fuels modern enterprises would be chaotic and inaccessible. In e-commerce, SQL is used to manage product catalogs, user accounts, and transaction logs, ensuring that every purchase, every user profile, and every item in stock is accurately recorded and easily accessible. For healthcare, it's critical for storing patient records, tracking treatments, and ensuring data compliance with regulations like HIPAA. In finance, SQL helps analyze transaction data to identify patterns, detect fraud, and generate reports that guide investment decisions. Social media platforms rely on SQL to handle user interactions, store content, and deliver personalized recommendations based on user behavior. These examples highlight how SQL adapts to the unique needs of each industry, making it a versatile tool for managing complex data ecosystems. SQL powers data warehouses, which are the central repositories where organizations aggregate and analyze large data sets to uncover trends and insights. Tools like Apache Hive and BigQuery use SQL-like syntax to process big data, allowing analysts to query vast amounts of information efficiently. This is crucial for businesses that need to make decisions based on real-time data. Business intelligence tools such as Tableau and Power integrate with SQL databases to create visual reports and dashboards, transforming raw data into actionable intelligence. Whether it's predicting sales trends or understanding customer behavior, SQL is the bridge between data and decision-making. Its ability to handle structured data makes it indispensable in the world of analytics. Performance is a common challenge in SQL, as inefficient queries can slow down systems. To address this, developers use techniques like indexing, which speeds up data retrieval by creating shortcuts to frequently accessed information. Partitioning divides large tables into smaller, more manageable pieces, improving query performance. Restructuring queries to minimize unnecessary operations also helps. Security is another critical concern, especially with sensitive data. Role-based access control ensures that only authorized users can access specific data, while encryption protects data both at rest and in transit. Scalability becomes an issue as data grows, but cloud-based solutions like Oz RDS and Google Cloud SQL offer flexible, scalable infrastructure that adapts to an organization's needs without requiring significant on-premise investments. Best practices for real-world SQL start with database normalization, a process that organizes data to reduce redundancy and ensure consistency. By breaking data into related tables, you avoid duplication and make updates easier. Transactions are essential for maintaining data integrity in multi-user environments, ensuring that operations either complete fully or roll back entirely to prevent partial changes. Regular backups are a must, as they protect against data loss from hardware failures or cyber attacks. Monitoring systems for anomalies or breaches helps catch issues early, while staying updated with emerging tools ensures that SQL solutions remain efficient and secure. These practices form the foundation of reliable, scalable database management. SQL is essential for managing and leveraging data in modern applications, from small startups to global enterprises. Understanding real-world scenarios allows developers to tailor SQL solutions that meet specific needs, whether it's optimizing a retail database or securing healthcare records. The key to long-term success lies in continuous practice and adaptation. As new tools and technologies emerge, staying current with advancements in SQL and related fields ensures that professionals can tackle evolving challenges. By combining technical skills with a deep understanding of business needs, SQL remains a powerful tool for turning data into value. Debugging is the process of identifying and resolving issues in SQL queries. When you write SQL, it's common to encounter problems that prevent your queries from running correctly or producing the expected results. These issues can range from simple mistakes to complex interactions between database structures. Common challenges include syntax errors, which occur when the query does not follow the correct structure of the SQL language, such as missing keywords, incorrect operators, or improper parentheses. Logical flaws are another category of problems where the query may run without errors, but returns incorrect or unexpected data due to mistakes in join conditions, filters, or the use of aggregate functions. Finally, performance bottlenecks can arise when queries take too long to execute or consume excessive resources, often caused by unoptimized queries, missing indexes, or retrieving large amounts of data unnecessarily. Effective debugging ensures that your queries not only work correctly, but also perform efficiently, which is critical for maintaining a responsive and scalable database system. Common query errors can be broadly categorized into syntax errors, logical errors, and performance issues. Syntax errors are the most straightforward to identify because they typically cause the query to fail outright. For example, forgetting to include a semicolon at the end of a statement, or using an incorrect operator like a plus sign instead of a logical and can lead to immediate errors. Logical errors, on the other hand, are trickier because the query runs without errors but returns incorrect results. This might happen if you accidentally join tables on the wrong columns or apply filters that exclude necessary data. Performance issues are often the most challenging to diagnose because they do not cause the query to fail, but instead slow down the database. For instance, a query that retrieves millions of rows without proper indexing can strain the system, leading to slow response times. Understanding these categories helps you approach debugging with a structured mindset, focusing on the type of error you are dealing with. To debug SQL queries effectively, you need to leverage a variety of tools and techniques. One of the most powerful tools is the explain or show plan command, which allows you to analyze the execution plan of a query. This plan shows how the database engine processes your query, including which indexes are used, the order of table joins, and the estimated cost of each operation. Database-specific tools like SQL Server Profiler or MySQL Workbench provide additional insights, such as tracking query execution in real time or identifying slow-running statements. Error messages and logs are also invaluable because they often contain specific details about what went wrong, such as missing tables or invalid column names. Another useful technique is to use print statements or DBMSOUTPUT to trace the values of variables during execution, which can help pinpoint where a query deviates from expected behavior. By combining these tools, you can systematically identify and resolve issues in your SQL code. Troubleshooting SQL queries requires a step-by-step approach to ensure you address the root cause of the problem. The first step is to validate the query syntax using a SQL formatter or linter. These tools can highlight formatting issues or syntax mistakes that might be overlooked during manual review. Next, test subqueries or parts of the query individually to isolate the problem. For example, if a complex query is returning incorrect results. Breaking it into smaller components can help identify where the error occurs. After that, check data types, constraints, and table relationships to ensure that the query aligns with the database schema. For instance, a mismatch between data types can lead to unexpected behavior, while incorrect foreign key relationships might cause joins to return incomplete results. Finally, monitor resource usage, such as CPU, memory, and I/O during query execution. This helps determine if the query is causing performance issues that need optimization. By following these steps, you can methodically address problems and improve the reliability of your SQL code. Adhering to best practices for troubleshooting SQL queries can significantly reduce the time and effort required to identify and fix issues. One key practice is to write modular queries with comments, which makes it easier to understand and debug complex logic. For example, breaking a query into reusable parts or adding inline comments to explain the purpose of each section can save time during troubleshooting. Another useful strategy is to use limit or top clauses to test queries with smaller datasets, which speeds up the debugging process and reduces the risk of overwhelming the database. Regularly updating statistics and rebuilding indexes is also essential for maintaining optimal performance, as outdated statistics can lead to inefficient query execution plans. Finally, documenting changes and testing in a staging environment before deploying to production ensures that any modifications are thoroughly validated. These practices not only improve the reliability of your queries, but also foster a more efficient and collaborative development workflow. Debugging SQL queries is a critical skill that requires systematic analysis and a deep understanding of the tools available. When faced with an error, it is essential to prioritize understanding the error messages and execution plans, as they often provide the most direct path to a solution. For instance, an error message might indicate a missing index, while an execution plan could reveal inefficient joins or scans. Consistent practice and adherence to best practices are key to improving query reliability, as they help you develop a proactive approach to identifying and resolving issues. Over time, this experience builds confidence in handling complex scenarios and ensures that your SQL code is both correct and efficient. By treating debugging as an ongoing learning process. You can continuously refine your skills and contribute to a more robust and performant database environment. SQL is a foundational skill in technical interviews and certifications because it underpins data manipulation, analysis, and decision-making across industries. Whether you're working with relational databases, big data systems, or cloud platforms, proficiency in SQL is often a non-negotiable requirement. To excel, focus on 4 key areas: writing queries that retrieve and manipulate data, optimizing those queries for performance, understanding database design principles like normalization, and solving complex problems by breaking them into logical steps. Mastering SQL not only opens doors to roles in data science, software engineering, and business intelligence, but also enhances your ability to derive actionable insights from data, making you a more versatile and valuable professional. Let's dive into the core concepts of SQL. The select statement is your gateway to retrieving data, but it's the join operations, inner, outer, and self, that allow you to combine data from multiple tables. For example, an inner join fetches matching rows, while an outer join includes unmatched rows from one or both tables. Subqueries enable you to nest queries within each other, solving more intricate problems. Aggregation functions like sum, count, and group by are essential for summarizing data, while having filters results after grouping. Indexing improves query speed. Normalization ensures data integrity, and foreign key constraints maintain relationships between tables. Clauses like where filter records, order by sorts them, limit restricts output, and distinct removes duplicates. Together, these tools form the backbone of effective data querying. Practice is where theory meets reality. Case studies involving customer data, sales, or user activity help you apply SQL to real-world challenges. For instance, you might analyze sales trends to identify top-performing products or track user behavior to improve engagement. Optimizing slow queries is critical. Using tools like Explain to examine execution plans can reveal bottlenecks. Edge cases, such as handling null values or duplicates, require careful consideration to avoid errors. Platforms like LeetCode, HackerRank, and SQL Zoo offer structured practice problems, while hands-on projects using real datasets build confidence. Remember, goal is not just to write queries, but to write efficient, scalable, and maintainable ones. Interviews often test your ability to think through problems step by step. For example, finding the second highest salary might involve using a subquery with order by and limit, or leveraging window functions. Understanding the difference between inner join and left join is crucial. The former returns only matching rows, while the latter includes all rows from the left table, even if there's no match. Retrieving unique records can be done with distinct or group by, depending on the context. A correlated subquery, which references the outer query's columns, is useful for comparing values across rows. These questions assess not just syntax knowledge, but also your ability to reason about data relationships and structure. Certifications validate your expertise and can significantly boost your career. The Oracle SQL Certified Associate focuses on Oracle databases, while Microsoft SQL Server certifications cover T-SQL and database administration. AWS Certified Database exams emphasize cloud-based solutions. Each certification has prerequisites, such as prior experience or coursework, and exam formats vary. Some include hands-on tasks. Resources like official study guides, practice tests, and online courses help prepare. Earning these credentials signals to employers that you're committed to mastering SQL, which can lead to better job opportunities, higher salaries, and recognition in the tech community. Success in mastering SQL requires a strategic approach. Start by creating a study schedule that allocates time daily for practice, ensuring consistency. Identify weak areas through practice tests and focus on improving them, whether it's understanding joins or optimizing queries. Cheat sheets and documentation serve as quick references for syntax and best practices. Collaborating with peers in study groups fosters discussion and problem solving, while online communities like forums provide support. Remember, the goal is to build a deep, intuitive understanding of SQL, not just memorize commands. Mock interviews simulate real-world pressure, helping you refine your skills. Practice under time constraints to mimic interview conditions, and record your solutions to review for clarity and efficiency. Feedback from mentors or communities highlights areas for improvement, such as simplifying complex queries or explaining your reasoning. Verbalizing your thought process aloud during practice builds confidence and ensures you can articulate your approach during actual interviews. The more you simulate, the more prepared you'll be to handle unexpected challenges. Leverage tools and resources to enhance your learning. SQL clients like MySQL Workbench, PG Admin, or dbeaver provide user-friendly interfaces for querying and managing databases. Free tutorials on YouTube, Udemy, or Coursera offer flexible learning paths, while books like SQL for Dummies and Learning SQL provide structured knowledge. Forums such as Stack Overflow and Reddit are invaluable for troubleshooting and staying updated on industry trends. Combining these resources creates a well-rounded learning experience, allowing you to tackle SQL challenges with confidence. Avoid common pitfalls that can derail your success. Forgetting to use aliases in complex queries leads to confusion, especially when referencing columns from multiple tables. Overlooking performance issues like full table scans can result in slow queries, so always consider indexing and query optimization. Testing with edge cases such as null values or large datasets ensures your queries are robust. Ignoring documentation for new features means missing out on tools that could simplify your work. Stay vigilant and proactive in addressing these issues to build reliable SQL solutions. To recap, consistent practice, a strong grasp of concepts, and effective resource utilization are key to mastering SQL. Apply your skills to real projects to gain hands-on experience and build a personal portfolio to showcase your work during interviews. Stay curious and keep learning as SQL continues to evolve with trends like window functions and advanced analytics. By staying updated and refining your skills, you'll position yourself as a proficient SQL practitioner ready to tackle any challenge. Keep pushing forward and remember that persistence is the foundation of expertise. Good day. Today, we will explore advanced SQL concepts that elevate your ability to work with complex data structures and optimize database performance. We will begin by examining subqueries, which are nested queries used to filter or calculate values within a larger query. These are particularly useful when you need to derive a value from a subset of data. Next, we will discuss common table expressions, or CTEs, which enhance readability by allowing you to break down complex queries into modular components. This makes your code easier to understand and maintain. We will also delve into advanced joins, such as self-joins and cross-joins, and their specific use cases. For instance, a self-join is ideal for comparing rows within the same table, while a cross-join generates a Cartesian product, which can be useful in certain scenarios. Additionally, we will explore recursive queries, which are essential for handling hierarchical data like organizational structures or bill of materials. Finally, we will touch on SQL optimization techniques, which play a critical role in improving query performance and resource efficiency. Subqueries are a powerful tool in SQL that allow you to embed one query within another. They are often used to filter data based on the results of another query or to calculate values dynamically. For example, a subquery might retrieve the maximum salary from a table, which is then used to filter employees earning above that amount. However, it is important to note that subqueries can become complex and difficult to manage if overused. This is where common table expressions come into play. CTEs provide a way to structure your queries by defining temporary result sets that can be referenced within the main query. This not only improves readability, but also allows for recursive operations, such as traversing hierarchical data like a company's organizational chart. When using CTEs, it is advisable to keep them concise and avoid excessive nesting, as this can lead to confusion and performance issues. By combining subqueries and CTEs effectively, you can create more maintainable and efficient SQL code. Window functions are a game changer when it comes to performing calculations across a set of table rows that are related to the current row. These functions allow you to rank, aggregate, or analyze data within specific partitions of your result set. For example, the ROWNUMBER function assigns a unique number to each row within a partition, while rank and DENSCRNK handle ties differently by assigning the same rank to identical values. The NTILE function divides the result set into a specified number of approximately equal groups. To define the scope of these operations, the over clause is essential. It allows you to specify the window of rows to consider, such as a specific range of dates or a particular group of records. A common use case for window functions is calculating running totals or moving averages, which are crucial in financial and time series analysis. By leveraging window functions, you can avoid the need for complex self-joins or subqueries, resulting in cleaner and more efficient queries. Query optimization is a vital aspect of SQL that ensures your database operations run efficiently. One of the first steps in this process is analyzing execution plans, which provide a visual representation of how the database engine processes your query. By studying these plans, you can identify bottlenecks such as full table scans or inefficient joins. Indexes are another critical component of optimization. A clustered index determines the physical order of data in a table, while a non-clustered index creates a separate structure that points to the data. Strategic use of indexes can drastically reduce query response times. However, it is important to avoid the habit of using select, as this retrieves all columns, which can be resource intensive. Instead, specify only the columns you need. Additionally, optimizing joins by ensuring that the join keys are properly indexed can prevent performance degradation, especially in large datasets. These techniques collectively contribute to a more responsive and scalable database environment. Transaction management is essential for maintaining data integrity, particularly when performing multiple operations that must be treated as a single unit of work. The acid properties atomicity, consistency, isolation, and durability form the foundation of reliable transactions. Atomicity ensures that all operations within a transaction are completed successfully or rolled back entirely. Consistency guarantees that the database remains in a valid state before and after the transaction. Isolation prevents interference between concurrent transactions, while durability ensures that once a transaction is committed, it remains permanent even in the event of a system failure. In practice, you will use commands like begin transaction to start a transaction, commit to save changes, and roll back to undo them if an error occurs. For example, when updating multiple tables to reflect a customer's order, a transaction ensures that either all updates are applied or none are, preventing partial data corruption. It is also crucial to avoid long-running transactions, as they can lead to locking issues and reduce overall system performance. Advanced joins and set operations expand the capabilities of SQL beyond basic joins, enabling you to handle complex data relationships. A self-join is used when you need to compare rows within the same table, such as identifying employees who report to the same manager. A cross-join, on the other hand, produces a Cartesian product, combining every row from one table with every row from another. While this can be useful for generating all possible combinations, it must be used judiciously due to its potential to create extremely large result sets. Set operations like union, intersect, and except allow you to combine or compare results from multiple queries. For instance, union merges the results of two queries while removing duplicates. Intersect finds common rows between them, and except returns rows from the first query that are not present in the second. These operations are particularly valuable when integrating data from multiple sources or performing data analysis tasks that require comparing datasets. Understanding when and how to apply these techniques can significantly enhance your ability to manipulate and analyze data. Adhering to best practices in SQL coding ensures that your queries are not only functional, but also maintainable and efficient. Consistent formatting, such as proper indentation and capitalization, makes your code easier to read and debug. For example, using uppercase for SQL keywords and lowercase for column names creates a clear visual hierarchy. Including comments in your code is another essential practice, as it helps explain complex logic or document the purpose of specific queries. Avoiding hard-coded values by using parameters or constants improves flexibility, allowing your queries to adapt to different input scenarios without requiring code changes. Regularly reviewing and refactoring your queries is equally important, as it helps identify opportunities for optimization and ensures that your code remains aligned with evolving business requirements. By following these practices, you can create SQL solutions that are robust, scalable, and easy to maintain over time. Even experienced SQL developers can fall into common pitfalls that lead to errors or inefficient queries. One such issue is the absence of a where clause, which can result in full table scans and unnecessary resource consumption. For example, an update statement without a where clause might modify all rows in a table, leading to data loss. Another common mistake is overusing subqueries instead of leveraging CTEs or joins, which can make your code harder to read and maintain. Additionally, failing to handle null values properly can cause unexpected results in conditions and aggregations. For instance, comparing a column with null using the equals operator will return no rows, as null represents an unknown value. To mitigate these issues, it is crucial to test your queries with small data sets before executing them on large ones. This approach helps identify potential problems early and ensures that your queries behave as intended. In conclusion, mastering advanced SQL concepts empowers you to tackle complex data challenges and build efficient, scalable solutions. By focusing on readability, performance, and maintainability, you can create queries that are both effective and easy to understand. Regular practice and analysis of query execution plans are essential for continuous improvement, as they help you identify areas for optimization. Applying best practices, such as using appropriate indexing, avoiding unnecessary data retrieval, and managing transactions carefully, ensures that your SQL solutions remain robust and reliable. As you continue to refine your skills, remember that the goal is not just to write functional code, but to create elegant, efficient, and future-proof database interactions. Keep exploring, experimenting, and learning, and you will become a more confident and capable SQL practitioner. And just like that, our dreamy coding adventure has come to an end. I hope the gentle ebb and flow of the tutorial, combined with the tranquil melodies, have left you feeling both informed and at ease. Whether you managed to catch every line of code or drifted off into a peaceful slumber, remember that the world of SQL will always be here waiting for you. Keep your code clean, your mind open, and your spirit relaxed. Don't forget to subscribe to Code Snooze so you never miss out on another soothing coding journey. Hit that like button if this video brought you a moment of calm and learning, and share it with fellow coders or anyone in need of a serene study session. Thank you for joining me in this cozy corner of the internet. Until next time, may your code run smoothly and your dreams be filled with brilliant algorithms. Sweet dreams, sleepy coders.